It's my pleasure today to have the opportunity to talk to you about smart civil structures. And today I will provide some of the lecture in English, and Sergio will provide some more specific examples as to what we mean by smart civil structures. Okay? And his will be in Spanish. So. Okay. So first, I want to tell you about Connecticut and where I'm from, just so you are aware. So in the US, Connecticut is a very small state in the northeast part of the United States. And so it is actually located, if you are familiar with the US, this is New York City, and this is Boston. So it's a very nice location between two of some of the best cities in the United States, New York City and Boston. It's in the New England portion of the United States, and we have about 3.5 million people in our state, so a smaller state. And this is what my hometown will look like in a couple weeks, in a few months in October and November. It's very pretty in the fall, so this is the best time to come visit us. But the University of Connecticut is the state university in Connecticut, and it is actually ranked the 18th top public university in the United States. So a very high ranking. It was established in 1881, and we have about 24,000 students located at various campuses throughout the university. And here are some pictures of the campus. So it is a pretty, and it's a somewhat rural campus. So my talk today, I would like to start out talking about smart structures and what do I mean by a smart structure or a smart civil structure. And what we will see is that a smart structure is actually defined by 4 areas. And there are sensors and sensor networks, information processing, so how do we process the information that the sensor is providing us, controllers, and actuating devices. So I want to talk to you a little bit about what are these areas and how do they relate to civil engineering in particular. And so as I said before, Sergio will provide you with 2 examples of some smart structures. One is an area we call bridgeway in motion, and the other is CCM, Connected Control Method for Base Isolated Buildings. These are some of the aspects of his Ph.D. research at the University of Connecticut. So, smart structures. What do we mean by these? This is a definition that is taken from Professor Zhang, who is now at the University of Maryland. But he identifies a smart structure or a smart structural system. Sometimes this might be called intelligent infrastructure. But it is an engineered structural system that has integrated sensor networks, information processing units, controllers, and actuation devices. And it does so synergistically, where it does so that these 4 systems are working together, that allows for the overall system, the structure, to respond adaptively to environmental changes. So maybe that's unclear, but this is the definition, and I hope by giving some examples, maybe this makes more and more sense. But the idea is to say it's a structural system that has these various components associated with it. And this is really the important thing here is it can sense its environment. And by its environment, we mean, is it currently in an earthquake? Has it received corrosion over the years and its structural system is somewhat compromised? Or what state is it currently in, and it can respond somehow to the knowledge that it has of its state. So the idea of a smart structural system originated back in the 1970s in aerospace and mechanical engineering. Okay, so our counterparts that are looking at aircraft, right, spacecraft, and mechanical components. In the 1990s is when this concept first began getting applied to civil structures. Okay, and so my particular background, right, is structural dynamics, and I became interested, very interested. I love the concept of smart structures when I went to graduate school back in 1996. So that maybe sets the tone for this. So I've been looking at these structures and types of structures for many years now. But why I'm so excited to talk to you guys about this is I see that while we've made many advances over the last 20 years, right, there's so much more potential in smart structures. So I am most excited about all of you students out here about what sort of things can you create with technology and moving forward. So oftentimes we see some realizations of smart civil structures as applications of structural control and structural health monitoring. And in fact, the two applications that Sergio will talk about today, the first is similar to a structural health monitoring, or it's a bridge monitoring application, and the other falls within the realm of structural control, controlling a structure physically. Let me show you some examples of smart civil structures, though. In civil engineering, the first real application of a smart civil structure, of structural control, was the Kobashi Seiwa building that was constructed back in 1989. Okay? So this was in Tokyo, Japan. This is the actual building right here, so it's a very skinny structure. And the concerns were with this building with impacts in a seismic event. The weak axis is so skinny that it might impact the building next to it. So to try to reduce the response of this structure in an earthquake, what was proposed was to put, and here's a schematic and a typical schematic that you might see of a smart civil structure or a structural control application, at least. It's difficult to see on here, but there are two actuators or active mass dampers, AMDs. You can see 1 and 2. It's maybe even harder to see in this picture here, but there's two AMDs. And an AMD, an active mass damper, is effectively a large mass that's sitting at the top of the building. And if we accelerate that mass in one direction, right, we know from Newton's second law that we're going to have a force that is reacting to that. So if we want to apply a force to the building in this direction, we can just accelerate the mass in that direction, right? And vice versa. So depending on how we accelerate this large mass on the top of the building, we can control the forces on the top of our structure. This is the idea of an active mass damper. So there are two active mass dampers, and there are sensors located on each of the dampers, so we know we want to accelerate it this fast, and we know for sure if we are or if we're not. There's an accelerometer at the top of the building, the middle of the building, and down at the base. So the building is aware of the excitation, the ground acceleration that is coming in, and it's aware of how it's already moving, right? So if a ground acceleration comes in, the building will start to vibrate. The building will start to move. And so if it's aware of the excitation that's coming in and how it's already moving, it can decide how it wants to move those masses to produce forces, to best reduce the responses. Okay? By the way, there are two masses up here so that we can control two degrees of freedom, or two directions of motion. One is the lateral motion, and the other is a torsional motion. So if you just had one AMD, you could control the response of the building going sideways, but it might start twisting on you. With two, we can now control both of those degrees of freedom, we would say, both of those directions that this building might move in. Okay? Okay, so this was built by Kojima Corporation. It's an AMD, active mass damper. The next application was in 1991, also in Tokyo, Japan. And this is a bridge tower for the Rainbow Bridge. So the Rainbow Bridge, during construction, the bridge towers are very susceptible to wind-induced vibration. Once the cables are on the bridge tower, it's much more stable. It's much more sturdy. But during the construction of that bridge tower, it's very susceptible to wind. And so during the construction, they placed on the bridge tower some active mass dampers. This is a picture of an active mass damper. So this is the size of it. It's hard to see the actual size, but these are fairly large because it has to produce enough force to control a bridge tower, right, or a building. And this structure, this is the mass that moves back and forth, and it's sitting on some rollers here, and down here there's a gear, there's a motor. And so that motor will spin in one direction or another direction in order to move the mass back and forth. Okay? So it's one thing to imagine, oh, I want to put a large weight on a building and accelerate it back and forth. It's another thing to actually try to build that or realize that. And that's oftentimes the challenges. So this was in 1991. This is another application in Tokyo, Japan, where at the top of the building were placed some hybrid mass dampers. And again, you can see two hybrid mass dampers to control the weak direction of the building and torsion. 1993, right, we have the Yokohama Landmark Tower, which is the tallest building in Japan. And on it, we have a hybrid mass damper as well. So this is a better picture to realize what is a hybrid mass damper. And throughout the presentation, I will return to some of these descriptions. But perhaps you know or have seen what is called a tuned mass damper. Have you, by a show of hands, who has heard about tuned mass dampers? Who has heard about Taipei 101? Building Taipei 101? Have you seen that? So if you Google or if you look on YouTube and search for Taipei 101, it is an extremely tall building in Taipei, Taiwan, and it has maybe one of the most famous tuned mass dampers on it. It's a large mass. It maybe looks similar to this. It's a large gold ball that is hanging from the top of the building, okay? And it is a pendulum, and it's tuned to vibrate almost at the same frequency that the building wants to vibrate, which a very tall building wants to vibrate at very low frequency or very long period. So it might take 5 seconds or more for it to vibrate back and forth. It's a very long time. So you can imagine the pendulum that you need to tune a pendulum, right? You tune it by frequency by changing the length of the fulcrum. So for a long period, you need a very long fulcrum for it to swing back and forth on. So For Type A 101, this works because the architect was bought into this and was excited about this, and it's a beautiful design component of the structure. But in general, a building owner might not appreciate if you as an engineer say, I need the top 20% of my building so I can reduce the responses. Those are the best stories, right? That's where you want your penthouse apartment or your expensive restaurant, right? You don't want a large mass that's moving back and forth. So two things that were done for this device. One is they used what's called a multi-stage pendulum. So they took this length and they basically broke it into smaller lengths and made it multiple stages. And it's very difficult to see or realize, but maybe you can see it, these sort of concentric rings. And they work, there's a frame that's attached by sort of a cable, let's say, that allows this thing to, in this short of height, act like a pendulum that might be 3, 4, 5 times longer, okay? So that was one innovation here. But the other, and why we call this a hybrid mass damper, is it's not just a pendulum that is going to oscillate based on the building, but it has small electric motors. So this electric motor here allows us to control the motion of this structure. So now we're not moving this entire mass, we're not completely moving it with the motor, right? The mass wants to start swinging a little bit because of it's on a pendulum, and we use the motor to either push it a little faster or maybe to slow it down a little bit, okay? So it uses a lot less energy to do something like this, okay? So this is this idea of hybrid. All we mean by hybrid is it's some combination of what we would call a passive device, or some device that'll work on its own, and it has some sort of active component to it, right? So this was the realization of a hybrid mass damper in Japan in 1993. So it's still very, very early on. Another hybrid mass damper. This is a slightly different realization of this. Here's a cartoon picture of this. Here is the TMD, tuned mass damper. And instead of having an actuator that's moving this mass back and forth, instead we put a mass attached to an actuator. An actuator is a device that's going to move this back and forth, and it's sitting on top of here. So a different way to add the active control to the passive control. Okay, Kojima was one of the companies in Japan that really pushed early on the idea of smart civil structures. This was in one of their buildings on their one of the research campuses. This is a type of smart structure where in the bracing, so this is some chevron bracing, and where it's attached at the top, it's not just welded or bolted in, but in between here, there is a device. And the device that's in here is a variable stiffness device. And so this device would have a valve on it that could change the oil column here, that it might be less stiff when the valve is open, but when you turn the valve closed, so when you actively close the valve, it shortens it up and it becomes more stiff. So you can change how stiff this frame is by simply turning this valve on and off. Okay? Again, it takes much less energy to turn a valve than it does to apply the force that the frame is applying to the building. Okay? And similar on all these pictures, I know it's very small and it's hard to see, but trust me, on all of these pictures, there are the devices. Here are 3 devices. There's always on these pictures, there are sensors. So you can see sensors located throughout here and control computers, right? So this structure has to know how it's reacting, and there's almost always a sensor down here. This sensor is on the base of this structure, not in the basement, but on the first floor, which is a sensor telling it what's the ground acceleration, and sensors throughout the building saying, how am I responding? And then a control computer that says, based on that, what do I want to do? Do I want these valves opened or shut right now? Okay? And that's the control part of that. This is also a Kojima building. And this building here, again, it's this 5-story building, had a semi-active variable orifice damper. So semi-active, it's a similar concept to hybrid, right? In that here, so here's the frames, only in the different orientation, right? Going down here. And at the base down here, we have these semi-active orifice dampers. And this is a picture of one of these dampers here. So this damper, to provide the force, we're not providing power to push hundreds of kilonewtons. Instead, we're providing the power to change a valve on here. So this valve changes from an open valve to a smaller valve. Okay, and as it does so, the damping, as the piston moves back and forth, fluid passes back and forth and the damping changes. So we can change in real time during an earthquake, as the building is moving, we can change that orifice. Okay? Okay. All of these applications, right, through 1998 here, were all in Japan. Okay? This was this was the first and one of the only applications of structural control in the US. And semi-active, this is a semi-active variable orifice damper that was implemented on a highway bridge in Oklahoma. Okay, and the damper is a small unit in here. This whole contraption and setup is so that we can take the small deflections. So bridges, when a heavy truck travels over them, they deflect, and they do deflect maybe more than you would like them to, but it's still a very small deflection. And so this frame here was set up to take the 2 rotations on this highway bridge underneath this girder and translate them into a larger motion across the damper. Okay? So this was an application of a smart structure in the United States. In addition to structural control, one of the other areas I talked about was structural health monitoring. One of the other realizations of how a structure can sense what it's doing, then it needs to do something with this. There have been many applications of structural health monitoring. I put these pictures up only because these are 6 permanently monitored bridges that we had in Connecticut. We had a 7th one, which was a wireless monitor, and then an 8th one that turned into our bridgeway in motion structure. But I put these up because I was involved in some of these applications. Okay? So these structures we'll talk more about, but the idea of vibration-based bridge monitoring is that we monitor the vibrations on a bridge, and oftentimes we want to monitor the ambient vibrations or the vibrations due to normal traffic loading. And from those vibrations, we want to say something about the condition of the bridge. So can the bridge say something about if it's healthy or not, right? To make it into terms that we're all familiar with, right? You wake up and oh, my head hurts, right? For whatever reason, but right? So how bad does that hurt? Do you need some medicine for that? It's the same idea for these bridges, is can we determine what is the health of the bridge? What is the assessment of the structural integrity of that bridge? Okay. So there's been quite a significant amount of progress on this. Last week at UConn, we had a professor from China who said there were 200 or 300 applications of bridge monitoring in China currently. So this has seen many, many different realizations. Another example, moving out of Japan, not too far from Japan, but to South Korea, was an air traffic tower. This air traffic tower that had hybrid mass dampers installed on them. This is a picture of the hybrid mass damper. We then have, in 2001, back in Japan, this was a museum of science and technology, and they employed a number of different dampers, but one of the reasons I have this up, or one of the dampers that were in this structure, was a Magnetorheological fluid damper. It's a type of semi-active damper. The previous semi-active dampers I described, we mechanically moved and changed the valve, right? The orifice in the valve, or shut it and opened it, okay? For this type of fluid damper, what we look to do is change something about the fluid. We can change the viscosity of the fluid. And Magnetorheological dampers, I'll tell you later today, I can show you some more pictures, but they have a unique property, which is when the fluid is put in a magnetic field, it stiffens up, the viscosity increases. So now, for this damper here, we just need to change the magnetic field through the area, through the orifice that it's passing through, and we can change the forces in that damper. Okay. And this is a picture of, this is now 2001, and this is a picture of the Triton Square office complex, three office buildings that were connected in Japan. And it's difficult to see, but there's a walkway bridge here. This is a picture of it. And a second walkway bridge here between the buildings. And the idea is that these three buildings can lean on one another. It's like three friends standing on a platform, right? And if you're all the same height and you're all the exact same, it doesn't do any good, right? If the ground shakes underneath you, if you're all moving the same direction the same way, well, then you all fall down, right? But if these are different heights, right, and they move at different frequencies, this is why it's good to have friends who are different than you, right? Is when you hold on to them, they can provide support, right? And they can react against one another. And what we find is, with very little forces between the buildings, we can reduce the response quite significantly, okay? So this was one application. This was part of my Ph.D. thesis, was looking at this concept. And Sergio is going to apply this concept to base isolated buildings as well. But it's called the connected control method. And this is another application, also another aspect of my PhD thesis, which was looking at cable vibrations and using these MR dampers to reduce cable vibrations. And this bridge, the Dongting Lake Bridge in China, had MR dampers that were installed. It's these two dampers installed on the cross bracing, two dampers, to reduce the vibrations of the cables. Okay? And the idea of using a smart damper here is if we just use a regular damper. So this is a good example of why is it better to be smarter? If you have to ask that question, right? Why is it better to be smarter sometimes? Well, for a cable vibration, you might imagine cable is very long. The best solution to reduce cable vibrations is to grab the middle of the cable, okay? This is also probably the hardest solution, right? How do you put a damper to the middle of the cable, right? It's also, some might argue, a very ugly solution, because these are beautiful structures, and if you tie them together with cables and netting, it looks messy, right? It's not as beautiful. So if you put a damper, if you put just a regular shock absorber, like in a car, right? If you put a damper down here, near the end of the cable, the only thing that damper knows is what is going on here at the end of the cable, right? Which could be fine if the cable is vibrating in what we would call first mode. Think of a guitar string, or how a rope that you have it if you swing it back and forth. If it's that half sine wave, then that's okay, right? That might be okay, because the damper is attached here, and if it knows the motion here, right, it might be related pretty well to what's going on out here. But if you have some higher mode effects, right, which would be like a full sine, right, or more, right, then what is going on here might not be related to the worst case scenario, what is going on in the rest of the cable, okay? So the benefit of a controllable damper is if you have sensors throughout the cable, or if you can predict with sensors what's going on at other parts of the cable, then you can react here based on what you know is going on out at the middle of the cable. Okay, so maybe it might not be best to react hard right now. Maybe you want to let it go to try to best understand, or to best reduce the vibrations elsewhere in the cable. So for longer and longer cables, semi-active devices or active and semi-active control become more useful in these cable vibration problems. Okay, so that takes us up to about 15 years ago. That was very slow progress. In the last 15 years, there have been many applications of structural control, of structural health monitoring, okay? So as the technology that we're looking at, that we're dealing with, as the sensor technology, as the computer control technology continues to increase, and as the devices that we're working with continue to increase, then the idea of smart structures continues to evolve and continues to transform, okay? Because 20 years ago, the sensors we were dealing with, or the computers that we had to take information in and do something with, they were very different than the computers that you have today, right? And in 10 years, right, the sensors, the computers that you will get to be working with will make today's computers look silly, right? I hope. So future smart structural systems, and that's why this is it's such an incredible time, right? Is these smart structures, they've come along, and they've come along quite a bit, and they serve their purpose when they can. But these future smart structural systems, right, the potential is very large, and they're gaining inspiration from the biological materials, okay, structures such as self-healing capabilities, and biomimicry, where you say, maybe our structures should behave as biological entities do, right? So maybe we should swim like a shark should swim, okay? What is the equivalent to standing like a building stands? Well, maybe we should be looking at trees, right? They tend to stand pretty well. But what can we learn as engineers for a built environment from what has evolved over time and what nature has learned, okay? So with that said, this idea of smart structures, we do seek to mimic these biological systems. And you kind of saw this from the term structural health monitoring, right? The idea was how do we turn this into sort of a person and a body here? But you can imagine that our structures, what we want with our structures are some sort of sensory, right? So how do we get about and how do we move? We have sensory. We can feel something, okay? That we know how it is. We can, if we've hurt ourselves, if we've twisted an ankle, we know there's pain, right? That we have, that we can tell, okay? We can also, from the sensory standpoint, if we think about our structures and we try to expand this, a lot of the senses that we have focus on sort of the touch, right? The idea of touch. So we can, and the physical feeling of this, right? We can have accelerometers that are telling us about the motion of a structure, or strain sensors that are telling us about the stresses on an object, right? And these are good ideas, and there are many advances that we can make in these areas. But we have many other sensors as well. We have the sense of vision, right? And I know there's some really neat research that's going on here at the University of Costa Rica on looking at how can we use vision-based sensors to determine how is this deflecting, right? And what might be the condition of our system. We can look at hearing. We were talking earlier today about can we use microphones to hear both. People have proposed oftentimes using microphones to hear cracking, right? And that distinctly sounds like I broke something, right? So can we hear what is going on? I'm not so sure if I know about the analog to taste. I don't know if we can do that, but maybe you guys can come up with good ideas for that analog. Maybe one thing, a structural analog to taste might be, in where I'm from, we get a lot of snow, and we put salt on the roads, right? And so we do have sensors that can measure the level of the salt that is put onto the roads. So that might be some analog to that. And what else? What other sense am I missing here? I think I've hit 4. Smell. Good. Smell. I don't know. This I put to you, right? So you figure out how we can use the sense of smell, right? Or what is the structural analog to that, okay? We also have a nervous system. The nervous system is, it doesn't matter that something touches you here, but you need to relay that information all the way to your central processing unit, right? To your computer, okay? And so that nervous system is your sensing system, okay? And how that gets that up to where you want to go. And it's your processing unit as well, how it gets that information up. We have a brain, which is what we're thinking about, and all those the applications, the pictures that we saw had control computers, or computers that are sitting there. That's maybe what we would say is the analog to our brain. And the brain is going to tell us what to do, right? So sometimes, right, if you touch something and you sense something's hot, then yes, you want to remove your hand as quick as you can, okay? But other times, you need to think about the reaction that you might have. So as a story, my son, who just started driving, his friend who was driving in his car, and a bee, an insect, came in, right? And so he reacted to it, right? And said, oh, an insect. And he hit a tree, right? But he needed to use his brain, right? And to think, I know that there is something here that isn't good, but the alternative is much worse, right? So it's okay if I get stung or bitten by this bee, okay? So we need to use our brain. We need to use a controller that says, I know that this might be happening, but maybe the bigger picture tells me it's okay. It's okay if this is receiving force or high stresses, because I need to protect the overall structure, or I need to protect this aspect of the structure, okay? And then there are actuating devices, or I'm sorry, there's muscular. Let's go from here. There's muscular, and the muscular is our muscles, right? How we actually move. If we know we want to pull our hand away from the fire, we need muscles to actually do that, okay? The same idea for a smart structure is, if we know we want to take some action, we need the ability to take that action, okay? So again, this is the analog here. And the smart structure too, to think about more than just reacting from systems. One thing that we had looked at as well was in a structure, so similar to a human, right? If you if you're playing soccer, right, football, and you turn your ankle, okay? What do? You probably, the first thing that you do is not, maybe the first thing that you do, but you probably don't just sit down and say, I turned my ankle, I'm done, right? Somebody get me. Probably what you do is you put some weight on it, right? And you say, well, how bad did I hurt this thing, right? Is it bad enough that I do need to fall down? Or is it okay that I can keep going, right? And so we've thought about in structural control the idea that if we have a structure that has sensors on it and has actuation, if we think that the structure might be damaged in an area, how might we actuate it? How might we move that structure in that particular area to actually see how bad is that damage, right? So this is, there are many things that we can take from just everyday life, and we can try to see, well, how could a structure benefit from behaving like that? But as you can see here, the idea of smart structures, right, is that we've got these areas of sensor networks, information processing, the structural system, right, and the control and the actuation. And it's sort of the combination of all of these areas that brings us into this area of smart structures. And what is interesting, and one of the messages that I would like to show to you today is what we traditionally learn in civil engineering is maybe just this portion down here. And maybe this is why you're a civil engineer and want to be a structural engineer, is because this fascinates you. And that's fine and that's wonderful. But there are these different areas, right? Information processing, sensor and sensor technologies, control theory and actuation that are important to maybe know something about, or at the least be aware that these are areas that you as civil structural engineers moving forward will probably have to interface with these areas in your career, okay? I would be almost certain that in your career you will have to deploy, employ, or take data from a sensor as a structural engineer, okay? And so understanding that what is that sensor and what is about it is, I think, important to realize. Okay. Are there any questions on this sort of smart structures overview? Okay, yes.
How has been the behavior of these structures in Japan, built since 1991 during earthquakes? ¿Cómo se han comportado las estructuras esas de Japón durante los siglos en el pasado?
That's a very good question, and I don't know. I don't know. Maybe I should, but the problem oftentimes is these systems were put into buildings that have owners, private owners, and a lot of times that information isn't available. So I have seen nothing in open literature that would describe the performance of those structures, of the actively controlled buildings. So, but a very good question. Okay, so now I'd like to talk about these four areas that I said make up a smart structure and provide you with some overview of these areas and what they're going through. So sensors and sensor networks, okay? Sensors, what is a sensor is a question, right? Well, maybe we think we know, but what is the actual definition of this, right? Well, sensors, they are the primary element in a smart structure. I would argue if you don't have sensors, then you don't have a smart structure, okay? because you need to be able to react to something, okay? Sensors in general, they are transducers that translate power from one form to another. That's very vague and right? It's not so clear. But here, what we want to do is we want to translate a physical phenomenon. We want to translate an acceleration, or we want to translate the stress in a material, right? Some physical phenomenon into an electrical signal, okay? Something that can run along a wire, okay, and be measured. So that's really what a sensor does, is it's going to convert something physical into some electronic signal. The physical phenomenon might be force, so it might be force-based, it might be an actual force that we're trying to measure, or it might be a pressure wave that we're trying to measure. It could be motion, which might be displacement, or velocity, or acceleration, or it could be, or strain, right? Or it could be temperature, or it could be many other things, okay? So 2 examples here, maybe say, I would argue that sensing elements, right, they commonly employ 2 different things. Either they're making use of electrical properties such as resistance or capacitance to convert a physical phenomenon to an electrical signal, or oftentimes they might be using piezoelectric material. And I'm not so sure if piezoelectric material, what the translation of that would be, or is it piezoelectric material? Piezoelectric material, we'll say. Okay, we'll talk a little bit more about this. But so 2 very common types of sensors that you might come across. One is a strain gauge. So strain is going to measure strain, right? And if we're in the linear region, then this is proportional to stress, right? So we can know the stress in a structure by measuring the strain. And the strain is the displacement, right, normalized by the length, okay? Delta over L, if you remember, okay? So how do we measure strain? Well, a foil strain sensor, this is a picture of a foil strain sensor, is a very common way to do this. And this sensor has conducting element. I don't know if you can see it kind of weaving back and forth, back and forth, back and forth. That's in here. This is maybe a clearer picture. This is a conducting element. And as this sensor is stretched, sensor is stretched, each of these little wires here is stretched, right? And as it becomes longer, it becomes thinner. There's only so much material that's there, right? So as it becomes longer, it becomes thinner. The cross-sectional area becomes smaller, and so the resistance increases. So all we have to do is measure the resistance between this point and this point, and it will tell us something about the deformation of our strain sensor, okay? So we can measure the resistance between these 2 points by hooking it up to a Wheatstone bridge. If you have an electrical circuits course that you might take, then you might learn this. You might learn more about, right, resistance and V equals IR and how all that goes together, okay? But this is one example of taking, and this is just using the resistance in a coil of wire and converting it into a physical specimen into some sort of electrical signal. Okay. The other common type of sensor that we might have is an accelerometer. So this is the case of an accelerometer. If you were to pull that off and look at what it looks like inside, they are very similar in nature, but this one has, in addition to all the other components in here, the critical components, let's see if I can see more clearly on here. Yeah. This orange piece here is piezoelectric material, piezoelectric crystal. Piezoelectric material is really neat. It's a really neat material. that if you apply a voltage to this, it expands, right? Or if you, a current to this, it expands, okay? Or if you apply a force to it, if you deflect it, if you make it a little shorter, it emits a charge, okay? It's pretty neat. So we can't power everything because, right, it takes probably more energy to try to deflect this thing than what you're getting out of this, right? But it emits a charge, and if it's under continued strain, that charge does decay over time, but it does emit in a charge. So what we do is we put a seismic mass, a large mass, on top of this material. So this is our base here. And if our base accelerates up, then that mass, same thing we talked about earlier, is applying a force. As it's trying to accelerate up, it's applying a force to this material, which provides a charge. So we just need to measure that charge, and that charge is proportional to the acceleration. Okay? So that's basically how accelerometers work. They might be different orientations, there might be piezoelectric material on the sides in a shear mode fashion, but this is the basic thoughts of how this works. Now, it's not so easy because you have a very small charge that you need to amplify and then you need to send out, but this is how we're providing this signal in a sensor. Here are some examples of bridges. I mentioned that we had some permanently monitored highway bridges, and I just wanted to provide some examples of how many sensors might we put on these bridges. Some people on a single bridge maybe have 300, 400 sensors throughout the bridge. That's a lot of sensors, okay? And depending on your application, you might want that. For the bridges in Connecticut that we looked at, this was and I apologize, these are in feet, but an 1,800-foot span, 5-span steel plate girder bridge. So it was this on this side, this is southbound side, this bridge here. It had a composite deck. And on this bridge, we had these sensors. So you recognize these 22 accelerometers that are measuring the vertical acceleration of the bridge. 6 tilt meters. This is a meter that as the bridge tilts, we can measure the rotation of that, or the rotation. And 16 strain gauges that were put onto the girders to measure this. And 4 LVDTs, linear voltage displacement transducers, and these are a mechanism by which we can measure displacement. And oftentimes these are put at the abutment to see, just with the change in temperature, what's the change in length of the bridge. This bridge here, this was a curved bridge. It had nine spans, I believe. Yes, 9 curved steel box girder bridge. So steel box girders, 2 of them. It had 8 temperature sensors. So temperature is very important to understand when we're looking at the behavior of these bridges. 6 tilt meters and 8 accelerometers. Okay. This bridge here was a shorter, more standard highway bridge. 3 spans, 3 simple spans of this steel girder bridge. So steel girders with a concrete deck on top of it. This one had 20 strain gauges throughout the steel girders and 4 temperature sensors that were placed on the bridge. And this bridge was a 3-span post-tension concrete box girder bridge, very large bridge for its purpose. It had 16 accelerometers, 16 strain gauges, temperature sensors, and tilt meters. So we use very common, basic types of sensors on these. Okay. Okay. So that's just an example of sensors and what kind of sensors are out there. Information processing, got maybe 5-10 minutes. Information processing. Are there questions on sensors? This is just an overview. There's so much exciting research being done just in the area of sensors and sensing technologies. okay? And the professors here can point you in different directions. You can look online in some journals, and if you can imagine it, right, there are sensors that are doing some of these. There are fiber optic sensors, and if you can imagine it and you don't see it, then you should still move forward with trying to realize this, right? But the idea of sensors and sensor technologies, they are quite expanding. Okay. So information processing. The idea here is to say, once we have sensors, we need to put it into some sort of format to make a decision, right? And you know this just from everyday life. You've got, if you yourself are getting information from, right, touch and sound, and maybe you're smelling stuff, right? You're getting all of this. You need to somehow collect this information, prioritize it, maybe get rid of some of the information because it's your little brother or sister talking to you about something when you're trying to do your homework about something else, right? So you need to filter some stuff out. You need to pay attention to other things, okay? And you need to process it so that you can make some sort of decision later on with it. So information processing, I would say, has these three general areas. Data acquisition. How do we take these electrical signals that are related to the physical phenomenon, what's going on in the building, and how do we actually turn them in from an electrical signal into something that our computer can do something with, which means we need to digitize it, right? We have digital computers, your iPhones, right, your phones, it's all digital. So how do we digitize this data? It sounds simple, and it's fairly straightforward, but we as civil engineers need to understand what exactly is going on, because if we don't do it right, we can have some real problems, okay? There's basic processing of the digital signals. This would be things like maybe we want to count how many cycles something goes through, or what are the maximum values of things, or without putting too much onto, maybe we want to think of things not in the time domain as something going, but we want to think of things in the frequency domain. If you've had in your math class, you probably have had Fourier transforms, which you thought as a civil engineer, that's not me, but it is you, okay? Fourier transforms, Laplace transforms, these are different ways we can think about data, okay? And in the area of smart structures, we like to look at things from a different perspective, a different view. Okay, so don't pay attention to those Fourier transforms in your class, right? Those are important. But the basic processing of digital signals, this is an area that is very, very detailed and a lot of information. We could spend weeks talking about just different ways that we might process the data, looking at mode shapes, calculating mode shapes, right, and comparing them to different things and different ideas. And then saving data for future use. This used to be a big issue, and it becomes, well, it's becoming less and less of an issue, but in the sense that when we started collecting data, to ask somebody to save a terabyte of data was basically to ask somebody to give you a room filled with computers, and it had to be cooled. And now a terabyte of data, that's no problem, right? Actually, it's probably hard to get a 1 terabyte hard drive. You probably would just go straight to the 3 terabyte hard drive, or the 5 or the 10 terabyte hard drive. Okay, so data, this is becoming less of an issue, although maybe the sensors we're creating and developing are saving larger and larger data. If I look back at digital pictures that I took 15 years ago, very small data sizes. Now, from my phone, much bigger, right? So, but I think we're outpacing. I think we're okay on storage. All right, so to briefly talk about some of the things with data acquisition. So these two areas, this is so complex. I just want to tell you it's out there, and be aware of this, right? This, I would say, I think we have this fairly well under control. I hope. I want to tell you a little bit about data acquisition because this is something as a civil engineer we often would say, it's no problem. I just plug the wire in and it shows up on my computer screen. No, this can be a big problem, right? There's numerous challenges. We could have data anomalies, aliasing, quantization, measurement noise, okay? What do we mean by each of these? Data anomalies, things like signal clipping. If I have an accelerometer, right, that in an earthquake it's gonna give this kind of motion, but I can only measure plus and minus 5 volts. Now I'm gonna get this, right? I'm gonna get something that looks like a flat top that is capped off here. We don't want to do that. We don't want to clip our signals, okay? We need to know what is the maximum acceleration that we might see. Intermittent noise spikes. The reality is you wire up a wire. If that thing isn't fixed down nicely and the connection's moving a little bit, you might actually want to see a nice signal and you might get, boop, right, a huge little spike up here because the wire is flopping around, okay? That isn't real. And as a structural engineer, you shouldn't change your structural design based on that, right? You should realize, hey, did somebody tighten the connector, right? Did somebody tape that down, okay? Signal dropouts. Oftentimes you'll have a signal going and then nothing for a little while. And then a signal going again, right? This can happen. Spurious trends. Many sensors are sensitive to temperature. And so just based on a strain sensor during the day, if it heats up, so maybe the structure heats up and it deforms, but in addition to that, if that sensor heats up, it might also deform, right? So your structure is doing nothing, but the sensor looks like, it makes the structure look like it's doing something, okay? And periodicities, this is oftentimes many of our structures have some magical motion at 60 hertz. I think is 60 hertz in Costa Rica? Yeah. So your structure is not moving at 60 hertz. You know it's oscillating at 60 hertz is the voltage coming from the power company, right? So if you don't ground your equipment well, then it's got 60 hertz sitting on top of it, okay? So please never design a structure that would vibrate at 60 hertz because that would be too confusing for us, okay? All right. Then there's things like aliasing. Aliasing is this idea that a signal, if you have this signal and you sample it too slowly, if you're only going to look at it here, here, and here, the signal actually might look like it's moving very slow. Aliasing, I believe a similar form of aliasing would be that if you look at, because a TV, when you watch TV, it's at 20 frames per second, right? So if you see, whether it be like a helicopter blade is oftentimes one thing they might see, you know that it's spinning really quickly this way, but it looks to you on the TV that it might be spinning very slowly. It might even be spinning backwards, right? You don't want to have that for your structure, right? You don't want to have it moving this way fast, but you think it's moving that way slow. That would not be good, okay? So, but understanding how do we not alias something, okay? We need to sample at sufficiently high rates. We've had discussions here, people have said, oh, we're sampling at 200 hertz, which is great, which is nice to hear. In general, you want to sample 10 times faster than the dynamics of interest that you're looking for. And then you want to employ what are called anti-aliasing filters prior to converting it from analog to digital and make sure that it's always there. These are practices that are commonly done, but not always done. Quantization. Quantization, again, this was an issue that maybe is resolved nowadays. How many bits do you have to represent that piece of data, okay? And it used to be 8 bits, 16 bits. Now things are 24 bits and above, right? And that's maybe sufficient number. But this is an example of quantization. This was a strain sensor on a bridge that this is what we were measuring. And we only had increments of, it was about one microstrain. And so this is what the response looked like previously. When we upgraded the system, this is actually right? The strain response that we were actually measuring. So there's a saying that says garbage in, garbage out. And if you bring this in and try to make a decision with something that isn't as good as it can be, then your decision will be limited by that data, okay? So, and then of course sensor noise. And sensor noise, if we have long wires, we can get a lot of noise. Many of the civil engineering applications that we look at, we're just measuring noise. The structures are so still many times, okay? Wind and earthquakes, they can move, but when they're still, all we see is noise on top of these. So we need to recognize it's noise and not try to react to that, right? So, okay. So this is an example. This was another bridge that we had. It's a single span bridge, simple span, that is steel girders with a concrete plate on top of it. And this is some picture of vehicles. This is the bridge itself. It's nothing fancy, but many of our bridges aren't fancy. They serve a good purpose. And this here is the strain that's being measured. We don't need the music, yeah. This is the strain that's being measured. And as you can see, when this truck, do you see this truck coming over? And it gave some strain to the bridge, right? And if we wait long enough, now there's no bridges, but this is our strain record as we move along. We want to wait for these two, right? That looks like something exciting is coming, okay? But as we move along now, we see a heavy truck, okay? 38,000 pounds, 73,000 pounds, a big dump truck that's coming over. And so we see these strains that are coming over this bridge. And so at this point, I'm going to stop talking and turn over to Sergio, who's going to show you and talk more about one of the examples that we had to look at, which is this idea of bridge way in motion. So one thing that we said was, look, when we have a small truck going over it, the strain isn't so large, right? When we have a heavy truck, the strain is larger. Well, how can we use just the strain to try to tell us what is the weight of the vehicles going over this bridge, right? And use the bridge itself as a sensor, okay? So before we go to that, are there any questions on some of the other things I've been talking about, sensors and the processing of the data? Again, it's areas in civil engineering that you didn't think you had to know, but at least you need to be aware that they exist. And the more you can know about them, the better you can communicate with your colleagues and the better you can design these systems. So, okay.
Muy buenas tardes. Quiero empezar por agradecer la oportunidad de estar acá. Es un gran honor para mí compartir con ustedes un poco de la investigación que estamos haciendo. Uno de ellos tiene que ver con la utilización de los puentes como instrumentos de medición, como estaba mencionando el profesor. Entonces, para esto yo quisiera empezar por proveer un poco de contexto, es decir, ¿qué es exactamente Bridge Weighting Motion? Algunos de los métodos que existen, por lo menos de los que nosotros estamos al tanto. Y en particular el método que nosotros usamos para este caso, que les voy a presentar, para luego ya entrar en detalles del ejemplo de aplicación, que es el que les traigo acá. Entonces, ¿qué es exactamente? Algún tipo de valor de respuesta. Y poder determinar algunas de las propiedades de los vehículos que están pasando sobre ese puente. Por ejemplo, cantidades de vehículos, distancias entre ejes, pesos de cada eje, pesos brutos en total de los vehículos, velocidades y otros más, ¿verdad? Entonces la pregunta es, ¿por qué hacer esto, verdad? Bueno, porque estas propiedades que estamos tratando de obtener son muy importantes para poder administrar la infraestructura vial de una manera adecuada. Y lo que pasa es que los métodos alternativos con los que actualmente pueden tener algunas limitaciones. Por ejemplo, el pesaje estático es muy preciso, nos da resultados bastante buenos, pero es un poco lento, ¿verdad? El camión tiene que salirse de su curso para poder entrar a la estación. Y además es susceptible a que exista a que los conductores quieran evadir este pesaje, especialmente si la carga con la que ellos vienen es mayor a la que tienen que tener, ¿verdad? Entonces ellos van a querer evadir este tipo de mediciones. Otra manera de hacerlo es con este tipo de tecnología que se llama pesaje en movimiento, en donde se colocan algún tipo de sensor, como el que se ve acá, ¿verdad? Esto es un ejemplo en Alabama, que genera muy buenos resultados, produce resultados confiables, pero el gran problema de esto es que hay que generar algún tipo de corte o excavación en el pavimento. Entonces, se induce un daño que tal vez no quisiéramos que esté ahí. Entonces, como alternativa, se propuso allá hace varios años, se propuso la idea de utilizar el weighting motion, pero en puentes. Y las ventajas es que podemos obtener resultados similares a los de weighting motion, pero son muchísimo más discretos, ¿verdad? Entonces podemos manejar mejor el problema de la evasión del peso y no hay que generar ningún corte o excavación en el pavimento. Este tipo de tecnología obviamente no es un producto acabado, pero y como tales tiene muchos retos pendientes. Por ejemplo, mejorar en el cálculo de las velocidades, lidiar mejor con presencias múltiples de los camiones, lidiar mejor con vehículos que transitan en diferentes sentidos, detectar vehículos livianos y otros. Pero esa es precisamente la labor de la investigación, de tratar de reducir la incertidumbre que se tiene con un método como este. Ahora, ¿cómo se realiza? ¿Cómo se lleva a cabo? Esto va a depender del tipo de mediciones que nosotros obtengamos del puente. Por ejemplo, tenemos, no sé, deformaciones unitarias o desplazamientos o aceleraciones o fuerzas, incluso otros. Como estaba diciendo el profesor, pueden ser, no sé, videocámaras o pueden ser micrófonos, no sé. Y también va a depender del tipo de procesamiento que le hacemos a los datos. Por ejemplo, existe una buena cantidad de métodos basados en líneas de influencia, en redes de neuronas, en algoritmos genéticos, en teoría de undículas y otros. Y en particular nosotros el que estamos utilizando acá es el método de área de influencia, con una pequeña variante que fue introducida hace ya algunos años. Y es precisamente a este último método al que yo me quiero referir acá. Algunas de las características de este método es que utilizamos deformaciones unitarias nada más, es decir, no ocupamos nada más que eso. Hay otros métodos que van a requerir varios parámetros al mismo tiempo, pero en este caso solo son las deformaciones unitarias. Fue desarrollado para puentes simplemente apoyados, entonces es una limitación que hay que tomar en cuenta. No se puede aplicar en puentes continuos. Se asume que la interacción del vehículo y la estructura no afecta significativamente en los resultados. Y aquí se presenta específicamente para calcular el peso, porque se pueden calcular otros parámetros como estaba diciendo anteriormente, pero estoy presentando acá simplemente para calcular el peso. Muy bien, entonces este método parte de un concepto bastante simple, bastante transparente para nosotros como ingenieros civiles, que es el modelo de una viga simplemente apoyada. Entonces, consideramos que el puente es como una viga simplemente apoyada que tiene una carga acá, en alguna distancia con respecto de los apoyos, y que genera una línea de influencia como la que se ve acá, específicamente para el punto medio. Entonces, con la teoría estructural convencional, nosotros podemos calcular que esta es la línea de influencia para el momento flexor en el punto medio del puente. Si asumimos que el comportamiento de este puente es elástico, entonces podemos extrapolar esto y obtener la línea de influencia de la deformación unitaria, que va a tener la misma forma que tiene esto, ¿cierto? Ahora bien, si nosotros asumimos que esta carga se mueve a una velocidad constante a lo largo del puente, entonces podemos pasar del dominio del espacio al dominio del tiempo. Entonces, pasamos de la línea de influencia de la deformación unitaria a la onda de respuesta de la deformación unitaria. Entonces, intuitivamente es bastante fácil imaginarse que la altura de este pico es proporcional a la carga P. Y eso se puede ver en esta ecuación que se ve acá. Tenemos una relación proporcional entre el pico máximo y la deformación unitaria que se mide en el tiempo. Eso sería suficiente si nuestros camiones tuvieran un solo eje, pero obviamente esto no es cierto. Entonces, lo que tenemos que hacer es aplicar el principio de superposición, ¿verdad? Ahora tenemos múltiples ejes viajando todos a la misma velocidad y por lo tanto entran y salen del puente en diferentes momentos y generan una onda de respuesta como esta, ¿cierto? Lo que pasa es que ahora la altura máxima de esta onda de respuesta ya no puede utilizarse como un parámetro para decir, bueno, este es el peso máximo. Pero sí lo que podemos utilizar es lo que se conoce como área de influencia. El área de influencia se define simplemente como el área bajo la curva de la onda de respuesta, que se muestra acá, multiplicada por la velocidad a la cual transita el camión. Entonces, esta expresión es proporcional a la velocidad y proporcional a la deformación unitaria. Y esta deformación unitaria, si recuerdan las ecuaciones anteriores, es proporcional a la rigidez del puente y al peso del vehículo. Entonces, si conocemos la rigidez del puente, ya tenemos todo para calcular el peso del vehículo. Lo que pasa, como ustedes bien saben, es que modelar la rigidez del tablero del puente es una labor que se las trae. Entonces, existe la alternativa de medir, de hacer una prueba experimental. Y si, por ejemplo, tenemos un vehículo con características conocidas, un vehículo del cual conocemos su peso, su geometría, podemos medir el cociente entre el peso bruto vehicular y el área de influencia que genera para calcular una constante de calibración a la cual le vamos a llamar beta aquí, que va a ser utilizada para estimar el peso de otros vehículos. Entonces, es una simple regla de 3. Es tan sencillo como eso. Entonces, como ustedes pueden ver, es un método que es muy transparente para nosotros como ingenieros civiles con la formación que traemos, pero al mismo tiempo muy útil, muy práctico, muy simple, y como les voy a mostrar más adelante, se puede implementar de una manera bastante rápida también. Ahora, aquí viene la variante que se introdujo en Yoakum hace algunos años, que es en el cálculo de la velocidad. Porque, como les mencionaba anteriormente, el área de influencia también depende de la velocidad y algunos métodos de los que nosotros conocemos lo que hacen es que miden la velocidad con otros métodos, pero aquí lo que estamos haciendo es que medimos la velocidad con la misma onda de respuesta. Entonces, una única medición nos da la velocidad y nos da el área, el área bajo la curva. Esta velocidad la calculamos de esta manera. Tomamos la diferencia entre los puntos TM y TF, que corresponde el punto TM al punto en el cual el último eje del camión se encuentra en el punto medio del puente, y el punto F, que es simplemente cuando el camión sale del puente. Entonces, la diferencia entre estos dos, dividida por la mitad de la longitud del puente, nos da la velocidad. Y se utiliza una constante de calibración, porque si estamos utilizando un camión que vamos a hacer pasar sobre ese puente varias veces, necesitamos asegurarnos de que la velocidad que estamos calculando sea exactamente igual o parecida a la velocidad a la cual el vehículo está efectivamente trasladándose. Entonces, en resumen, lo que nosotros hacemos es, primero, medir estáticamente el peso de un vehículo con alguna geometría. Le medimos la geometría, los pesos de cada eje. Hacemos transitar ese camión sobre el puente y medimos su área de influencia. Con esa medición calibramos las constantes K y beta. Luego medimos el área de influencia de los vehículos desconocidos y ya con eso podemos calcular el peso y la velocidad. Insisto, es un método bastante sencillo y yo creo sinceramente que es bastante práctico. Entonces quiero mostrarles acá un caso bueno, antes de mostrarles el caso en particular, quisiera hablar de cuál es la manera de implementar esta metodología. Nosotros desarrollamos un algoritmo que está escrito en MATLAB para poder automatizar esto, porque la idea es hacer esto de la manera más automática posible. Entonces, este algoritmo incluye, por ejemplo, el primer paso es eliminar el ruido. Entonces, por ejemplo, este es un pasaje de un camión cualquiera y ustedes pueden ver que la señal, antes de filtrar el ruido, contiene este componente de alta frecuencia, y una vez que se le aplica el filtro, ya tenemos un valor mucho más limpio. Eso es particularmente importante para poder calcular los puntos TF y TM de los cuales estaba hablando anteriormente. Entonces, como estaba diciendo el profesor, es importante la parte del procesamiento de los datos. También existen sesgos por temperatura, por ejemplo. Entonces, como ustedes pueden ver acá, lo dramático que puede ser el sesgo por temperatura. En un lapso apenas de 10 minutos tenemos una diferencia de 100 microstrains, y entonces es necesario utilizar técnicas para poder eliminar estas tendencias y poder hacer de nuestra medición tener una línea base un poco más uniforme. Entonces, por ejemplo, aquí una de las maneras de hacer eso es aplicar un filtro pasa altos, en donde vamos a quitar los componentes de baja frecuencia, y con eso podemos hacer que nuestra línea base sea más uniforme. Y esto es muy importante para el siguiente paso, que es identificar lo que nosotros le llamamos camión, porque ustedes pueden ver acá que hay un montón de picos en nuestro registro, pero ¿qué le llamamos camión? ¿Cómo podemos saber eso? Entonces, una manera de hacer eso es con base en la experiencia y ya mediciones anteriores, determinar un valor límite, que en el caso en que yo les voy a mostrar fue de 10 microstrains, y decir, a partir de aquí yo voy a analizar, y lo que está debajo de eso por ahora no lo voy a considerar. Entonces, hay que identificar primero los camiones. Una vez que están identificados los eventos de camión, hay que decidir en cuál carril se está trasladando. Entonces, si tenemos un puente con múltiples carriles, probablemente vamos a poner múltiples sensores, uno por cada carril, para poder comparar el valor máximo de cada uno y decir, bueno, si está en este carril o está en el otro, o en el tercero. Y entonces se le aplica el valor de calibración correspondiente a ese carril en particular. Entonces, esto también es muy importante. Una vez que ya tenemos este paso, podemos definir una ventana para cada evento de camión, es decir, yo identifico el pico máximo y defino, bueno, de aquí para atrás tanto tiempo, de aquí para adelante tanto tiempo, y eso es lo que yo voy a usar para analizar. Con esa ventana definida, entonces ya podemos ir y buscar nuestros puntos TF y TM, o al revés, TM y TF. Y esto es lo que nos va a dar la velocidad, como les estaba diciendo anteriormente. En algunas ocasiones hay situaciones que son, bueno, difíciles de manejar. Por ejemplo, que hay dos camiones trasladando muy cerca uno del otro, o que están cambiando de carriles. Entonces, a veces el cálculo de las velocidades simplemente se vuelve loco. Entonces, tenemos que deshacernos de esos valores para poder hacer una estimación racional, ¿verdad? Entonces, velocidades que están fuera de los límites racionales, entonces no las tomamos en cuenta. Una vez que ya tenemos la velocidad, calculamos el área de influencia. Obviamente en la parte teórica se habla de una integral, pero esto es en el tiempo discreto y es una suma, como se ve acá. Y finalmente se calcula el peso de cada uno de los vehículos que acabamos de identificar. Entonces, como les decía, este algoritmo se desarrolló en MATLAB y se trata de aplicar lo más automáticamente posible. Quiero mostrarles acá la prueba de campo una de las pruebas de campo en las cuales hemos aplicado este método, lo hemos aplicado en varios. Es en una ruta estatal que está acá y es la que se muestra en esta fotografía. Es un puente de 2 carriles y un espaldón con la geometría que, bueno, lamentablemente no sale muy bien acá. Y tiene 8 vigas de concreto preesforzado. Y nosotros ubicamos dos sensores, uno por cada carril. Entonces ven que ustedes, para este carril tenemos un sensor que es este, y para el otro carril el otro. Entonces, lo que hicimos fue que se coloca el sensor debajo del puente, en una de las fibras inferiores de la viga. Este sensor está conectado vía un cable a un nodo que transmite esta información inalámbricamente a una estación base que está a la orilla del camino, que a su vez transmite la información a una computadora que ya podemos usar para el procesamiento de los datos. Entonces, esta instalación es bastante sencilla. En realidad nos tomó como 2 horas y media hacer toda la prueba. Entonces ustedes pueden ver que es bastante práctico. Algunas de las características de la adquisición de datos las muestro acá. No voy a entrar mucho en detalle de eso. El vehículo con características conocidas es el que se muestra acá. Aproximadamente 25 toneladas métricas, con la distribución de los ejes como se muestra acá. Y como les decía anteriormente, información obtenida previamente de otras mediciones, o sea, de una medición estática. Se hace transitar este camión varias veces por un carril y varias veces por el otro. Y con eso podemos calibrar las constantes de las que estaba hablando anteriormente. Algunos de los criterios que se usaron para el algoritmo fueron, por ejemplo, el filtro pasabajos, quitar todo lo que está encima de 15 Hz. Filtro pasaaltos, quitar todo lo que está debajo de 0.004 Hz. Utilizar la deformación unitaria mínima de 10 microstrains. Y el segundo pico, que es el que yo defino para el último eje del camión, de 7.5 microstrains, como se ve acá. Entonces, aquí hay algunos de los resultados que se obtuvieron para la calibración de las constantes para el carril 1 y para el carril 2. Yo quiero destacar aquí, me parece muy importante decir que se repite muy bien una prueba con la otra. Esto es muy importante, tiene que ser repetible. De otra manera, si cuando pasa el camión genera una onda de respuesta totalmente diferente, entonces eso es preocupante. Entonces es muy repetible, genera valores de calibración que están bastante cercas unos de otros y podemos aplicar, no sé, un promedio tanto para acá y para beta. Y cuando aplicamos estos valores, estos de acá, en el cálculo del peso del camión, entonces obtenemos valores que están muy cercanos a los teóricos. Entonces, esto genera confianza, ¿verdad? Esta metodología se ha hecho, bueno, estos resultados son para el camión de peso conocido, pero se ha hecho la comparación también en otros ejemplos para camiones con valores desconocidos. Es decir, se pesan los camiones en una balanza estática y se comparan, y han dado resultados bastante buenos. Ahora, ¿qué se puede generar cuando uno aplica esta tecnología, ¿qué se puede generar? Por ejemplo, un histograma de velocidades. Esto es uno de los productos que obtenemos utilizando esto. Vemos que, bueno, como les decía, 2 horas y media y ya tuvimos todo esto. Pudimos identificar 58 vehículos en total, con velocidades que oscilan entre los 64 y los 140 kilómetros por hora. Esta velocidad podría sonarles muy alta, pero es una calle cuyo límite es de 65 millas por hora y no es nada extraño ver vehículos circulando a velocidades tan altas como 90 millas por hora. Entonces, si bien es cierto, tenemos algunos valores un poco altos, no es raro ver eso en la vida real. Y la velocidad promedio fue de 110 kilómetros por hora, muy cercano al límite de velocidad, como ustedes pueden ver, que es de 65 millas por hora. También podemos generar histogramas de pesos. Esto es una distribución bimodal, más o menos centrada en los 55 kips o 25 toneladas métricas, como por acá, y la otra parte centrada como por acá, y 22 vehículos de los que identificamos con un peso mayor que el permitido. Entonces, de nuevo acá, uno dice, bueno, 40% de los vehículos tienen un peso mayor que el permitido, eso suena alto. Entonces, lo que yo digo es, bueno, para poder saber si eso es cierto, hay que investigar un poco más. Pero con solo que a uno le diga a la administración, bueno, 40% de sus vehículos tienen sobrepeso, yo considero que esto es muy valioso, ya con solo esto. Porque ya invita a la gente a decir, ¿será cierto esto o no? ¿Verdad? Porque esto es alarmante. Entonces, bueno, ese es uno de los puntos que quiero hacer acá. Otro situación que uno es bueno verificar es que no haya ninguna relación entre peso y velocidad, porque queremos eliminar tendencias maliciosas ahí en los datos. Entonces vemos que el coeficiente de correlación es bastante bajo. Entonces estos son básicamente los productos que podemos obtener, y otros en realidad, pero aquí estamos mostrando solo algunos. Entonces eso es lo que quería presentarles por hoy. Más adelante les voy a presentar otro ejemplo relacionado con el tema del control.
Very vague because it can mean many different things. For bridgeway in motion, right? If we have this information, if we know the weights of a vehicle traveling over the bridge, right? What sort of things might the bridge, right, be able to do? So it could do some things, like it might alert enforcement to say, hey, there was a very heavy truck that just went over me, right? You should look for this. Or oftentimes, trucking companies, at least in the US, they run in very regular patterns. So maybe we can say, on Tuesdays and Thursdays at 3 a.m., there's always a heavy truck, right, that's coming over, so we should go look at this. But it might alert that. We could think about things that the bridge, maybe if the bridge has received so much heavy traffic in the slow lane for this month, maybe it says, I should divert traffic to another lane, okay? So maybe the control could be something along those lines where it says, let's have the heavy weight go elsewhere. Or maybe it says, I'm done for the year, right? I've had enough heavy traffic, I need to protect myself, right? Or it could simply say, instead of closing down bridges is not really an option, so maybe it says, I need some maintenance. Okay, I know that I've received so many cycles of heavy trucks crossing over me that I can predict that I've got critical components that are receiving fatigue. Okay, and if it's got sensors on it, maybe it can also identify have things structurally changed that I have started to fatigue some areas. Okay, This is one general area of control that you can think of, and it's more of this idea of some logic that we would set up. A seismically excited building, like many of the structural control applications that we looked at, what we're talking about doing is controlling forces, the forces that we want to apply. It's either an AMD, one of these masses that we're going to accelerate up on the top, or it could be some actuators that we want to push on the building. But we can apply forces in the structure or to the structures that would either redistribute the loads and the energy or dissipate the energy, right? So we're going to either dissipate or redirect the energy that's coming in from the earthquake or coming in from the wind, okay? So this area here, this concept, is what we might call more formally structural control. Okay, so it's not just control, but it's structural control. And this is an area that for smart structures, it involves sensing the environment. And again, the environment isn't necessarily the environment around us, right? The water and the trees, but the environment meaning earthquakes, the wind, the excitations that are occurring here. And perhaps sensing the condition of the structure, and then applying an appropriate reaction, right, to any further input energy, okay? So it's an extension of standard structural control. So for a smart structure, it's an extension to structural control that uses passive means, okay? And it includes the sensors and the actuations. Those examples that I showed earlier, they all had sensors on them. They all have control computers, which is what we're talking about here. And then they all have the means to apply some sort of force, okay? And so what we're talking about for smart structural control would be active or hybrid or semi-active types of control. So in general, if we think of our structure, so here we have a structure that's sitting here, and we have some excitation. So maybe this is a ground motion, a ground acceleration, or earthquake, or maybe this is wind, or maybe this is waves, but it's something that's exciting our structure, okay? And so what you learn then is when you have a dynamic force acting on a structure, you get some sort of dynamic response, all right? You get some response. There's an earthquake and the building is going to sway back and forth and move back and forth. So types of structural control, the one type which is not smart, but it can be very helpful and useful, is passive control systems. And in passive system, we would fix some passive device to our structure, okay? And these examples of these might be like putting a damper in a building, right? Cross bracing or in the bracing of a building, or base isolation, taking our building and putting it on isolators so that the ground moves underneath it and the building stays the same, or putting a tuned mass damper, putting a mass up on the top that's like a pendulum, tuned to be like a pendulum that vibrates, and the vibration of the mass is going to suck energy away from the structure, okay? So these are examples of passive control. But to talk about smart structures, right? Here, instead of that passive energy device that's applied to the structure, we're going to have an actuator that is going to apply a force to the structure. And that actuator, right, is going to, it's going to be something like active bracing. So maybe this, instead of being just a damper, a shock absorber like in your car, this is a motor, right, that can actually apply a force. Or it's a hydraulic actuator that can push back and forth and apply forces, okay? We would have a sensor up here on this, or we could have an AMD, like I had shown you previously, a mass that's here that has a gear, a motor with a gear that's going to throw the mass in one direction or the other and create these forces back and forth. So for these setups, what we need for this full system are sensors, right? We need sensors and we need a controller. So the actuator needs to know what to do. The controller can tell it what to do, but the controller itself needs to know what is the excitation, right? What is the excitation, and what is the response of the structure, okay? If we look here, we can see there's a couple different loops in here. This is one loop that's coming forward here, and then you get a response that comes out over here. This is called a feed forward loop because it's moving forward in this direction that we have. You're going from the excitation, you're measuring that excitation. This is why there were the accelerometers down at the base of every building, because you're measuring the input, and that's feeding forward into the structure where you're deciding what to do. The other alternative here is what's called feedback. You measure the response of the structure. You're measuring that the structure is moving, and you're telling the controller, structure moved. What should I do now, right? So both of these have positive aspects to them, okay, and can have some drawbacks to them as well. And various combinations of these might be employed. And we'll take a look more at this case. But the idea of the hybrid control system, if you remember some of those examples I showed of hybrid control, is here we have an actuator, but we also have a passive device. And so that actuator is working in conjunction with, so let's say we have a base isolated structure, but we might also have an actuator acting on that base isolated structure, okay? This would be hybrid because it's both active and passive elements that are being put together. And then if we have the actuator that's acting on a passive device, so this is the case where you have a damper and where the actuator is changing the valve, right? Changing the size of the valve or turning it on and off. That's where the actuator is acting on a passive device. This is what we would call semi-active, okay? These are these cases. But you can see in all of these cases, we have this general framework where we have a feed forward and we have a feedback loop, control. So these are control loops. This area then gets into the area of control theory, which sounds exciting, and it actually is very exciting. But I would warn you also that it's like learning a whole new language or a whole new way of seeing the world, okay? When we interact with our mechanical engineering and electrical engineering counterparts and we say, oh, you call it that, I call it this, right? Oh, right? Even some simple things like imaginary number is I, no, it's J, right? Or a Fourier transform, mine has a 2 pi in it, yours has no 2 pi in it, right? It's the same world that we live in. It's just different ways to talk about it and view it, okay? All right. So what I'd like to talk a few minutes about then is this idea of a controller, okay? And what do we mean by that, and what are some areas that we can think about with that? So, automatic control systems, as I said, typically this is an electrical or a mechanical engineering subject, but my students, which I am in a civil and environmental engineering department, and all of the students, graduate students that come work with me, they learn this, and it might be painful a little bit, and they have to take a couple courses so they can learn how to talk and work in this realm. But this is something that civil engineers can and should learn. In general, control is used for these 5 different areas. To reduce sensitivity to variations, okay? Which for us, if we go back to like building cases here, this could be that the response of our building, maybe we have some uncertainty in the structure itself. So you might tune a TMD for one structure that's behaving one way, but maybe there's some variation in that, right? If you had a control loop, that would add more robustness to that control. Reduce sensitivity to disturbance. This means it can reduce the sensitivity to a disturbance meaning an earthquake, right? That it makes our system less sensitive to vibrations from wind or vibrations from external sources, which would be like an earthquake. Ability to control system bandwidth. This terminology maybe seems a little foreign because it is, right? But bandwidth is this idea of if we think of things in the frequency domain and being able to control our system in that frequency domain. Maybe that seems something that you don't need to worry about, but when we look at the spectral energy of an earthquake, right? We're looking at the energy of an earthquake over a frequency range, over the period, but if we invert that, now we're looking at frequency. So we have the ability to perhaps control the building in different frequencies and put more emphasis in areas where we know earthquakes might come in at, okay? Stabilization of an unstable system. Hopefully all of our structures that we build are stable to begin with, but who knows, after a major earthquake, we might have some potentially unstable structures that a control system might be able to provide stability for, okay? And then control transient responses, which would be responses to large earthquake ground motions that are coming in, right? So, anyway. There are different types of control. One is open loop control, and this would be similar to that feed forward loop without the feedback loop. And the idea is that you have a desired response, right? That goes into your controller. It's thinking about what to do, and it's going to then command the structure to do something, and you get the response that you want. For civil structures, usually our desired response is 0. Usually we don't want the structure to move, right? That's easy. I want 0. What am I going to have to do so that I actually get a response which is 0, which is nothing, okay? Mechanical engineering structures, it might be a robotic arm wants to go pick something up here and move over there and put it down, right? But this is our case here, is we have some desired response and we're going to command so that our structure actually gives us that response. Now, to try to make this mean something more to you, I'm going to use an example which comes from, it's an adaptation of an example from Rohr, which is a pretty popular controls textbook. And the example is filling a sink with water. I don't know. Maybe you filled a sink with water. Maybe you're doing dishes or you're getting ready to shave. If not, if you've never done this, then maybe tonight go home and fill a sink with water and try this, okay? You have some options to do, right? Open loop control. Open loop. You would open, and I'm assuming that the sink has a hot water and a cold water spigot, right? So you open the hot water tap, some specific amount. You open the cold water tap, some specific amount, right? 2 turns, half a turn, and you're good, right? And you fill this sink up. That works sometimes, right? That works if you've done this many times before, okay? So every night you do this, okay? So you're good. You know it's 2 turns here and a half turn there, and you're good to go, right? So you know these settings, right? However, a number of factors might affect this. One is that maybe your little brother or sister just took a very hot shower and there's less hot water now, right? So maybe it needs to be 4 turns on the hot water and a half a turn, okay? Or maybe you're not doing this in your sink, right? Maybe this is somebody else's sink that you're filling this up and you don't know what their temperature is, okay? So all of these cases, you can still go in and do 2 turns and a half turn, but you don't know when you put your hands in that water if it's going to be too hot or too cold, right? So this is the issue with open loop control, and it's open loop because we're just moving forward, right? We're not using any information okay? This is now the idea of, here we have a desired response that goes into our controller. Here's our control command that we're sending out to our structure, okay? And we get some sort of response. Now, if we take that response and we feed that response back to our controller, now we've closed the loop. So this is a loop, right? So now we've got a closed loop controller, okay? And this closed loop controller, it uses these feedback measurements. So we have to be able to measure the response or measure other aspects of the state of our structure. So for the same example of filling up a sink with water, right? If we want a specific temperature here, right? In a closed loop control, feedback measurements are included to achieve the desired response. What is a feedback measurement? Well, for this case, it might be sticking your finger in the sink, right? And saying, "Whoa, that's cold," right? We need some more hot water, okay? Or that's not so cold, right? And being able to base off of that. So you're using a feedback measurement, okay? You might want to feel the water at several different times. So how often are you going to sample this system? If it takes you 2 minutes to fill the sink up, are you going to sample it once at 1.5 minutes? Maybe. You might get some results. If you're going to sample it every 5 times a second, right? Maybe that's too much, right? But there's probably some good sampling rate that you can use so that you end up with some good tracking, some good response, okay? If the water's not at the right temperature, you're going to adjust the hot or the cold water faucet. So that's your actuation then, right? Okay? So in this manner, the system output affects the control, okay? So now it's okay if there isn't a lot of hot water in the system, you can account for that. Or it's okay if you go to somebody else's sink, right? You can account for that, right? You're going to feel the water, you're going to base it off of that. But there are many things that this example sort of shines the light on, which are basic things that we are concerned about in control, which are, we talked about the sampling rate, or what do you want to sample, right? Are you going to sample the water as it's coming out of the faucet? Are you going to sample the water in the sink itself, and is it at the back end of the sink or the front end of the sink? Because there's a temperature change in there, right? There are many of these issues. There's also the issues of, I don't think it's here. Yeah. Okay. We'll get to it here. But the use of the state of the output is termed feedback. And so this is our feedback control. The more measurements that we can take, right, the temperature of each faucet, the rate of change of the temperature. So maybe it's not just what's the state of the temperature, but maybe if you're checking it every 5 seconds, okay, a little compulsive, but every 5 seconds, maybe you're also not just considering what is the temperature, but how quickly is that temperature changing? Okay, and if it's changing real fast, well, I should back off a little bit more, right? If I know I want to get to this temperature, I want to gradually get to that temperature, right? I don't want to quickly go up. So I'm going to overshoot, quickly go down, up and down, okay? It may be more complex, but it can provide better performance, okay? So, if you have additional inputs, it can help to achieve a desired response if additional inputs are provided. So if we think of our building, right, as this, or this sink as our building, if an earthquake would be if somebody with a pitcher of ice water, right, dumps a pitcher of ice water in. That's an earthquake, basically, to our building, okay? And by doing this, by measuring this, we can account for this, right? We can crank up that hot water and we can deal with this as best we can, as quickly as we can, to get to our zero response that we would like to see, okay? And of course, if we think about this too, there is this compromise between stability and performance, okay? And that's maybe something that's not completely obvious, but as you're adjusting the water in this sink as it's filling up. If you want good performance, which means you want to, if it's too cold, you want it to get very hot very quickly, okay? Then you're gonna turn that faucet on all the way if it's too cold. And oops, it got too hot. I'm gonna turn that off and turn that one all the way up, right? And that could work, but you could have issues with stability. You could end up with the sink that's getting really hot and really cold, really hot and really, it depends how good your measurements are and how quickly you are at turning faucets. If you can turn them real quick, that's great. If it takes you, right, 4 or 5 seconds to get that thing turned, then you could be in trouble and you could have these wild oscillations, okay? And in fact, you could end up with a system in the control area that we would say is unstable, okay? I don't know what that looks like in your sink, but in responses, it means that something goes wildly out of control until it fails, okay? So this is this idea of structural control, and this is a little bit more of this idea between stability and performance, okay? And it has to do with delay and the gain at which we want to do this. So this is us as a human controlling this. If we want to take the human out, it's probably not a good idea to say a smart structures has you as an engineer sitting in the building looking at things and turning knobs, right? Let's get away from that. And so we want to take the human out of this closed loop. And we want to make it what would then be called automatic closed loop control, okay? We need sensors to measure the required variables, right? Or the things that are required. We might use accelerometers to measure acceleration. We might use strain sensors to measure the strain on certain members, okay? But these are the sensors that we have. And we will need actuators to actually control the valves. These would be devices that can actually apply the forces to the different parts of the structure that we're interested in, okay? And then the controller itself that's going to interpret these sensors and send a command to the actuator, okay? So this is the controller. We're not going to talk much more about controllers because this is, there are courses on this and multiple courses. Sergio has an example where he's going to apply a somewhat sophisticated type of control. A basic controller that you come across many times would be called a Pid controller, okay? And it means that what you look at is the response and your desired input, and you look at the error, the difference between those two, and then you say that error, right? Pid, proportional, I'm going to take that error and I'm going to multiply it by some gain, and that's going to tell me what to do, right? Or the D is the differential. I'm going to take that error and I'm going to take the derivative of that error, and based on that, I'm going to apply some gain to that, and that'll tell me what to do. So what that, the P and the D part tell you is how far away are you from where you want to get, right? And the further you are away, the proportional part is going to tell you have a lot of change to your system, okay? And then the other aspect of it is going to say that that as you're getting closer, right, if your rate of change is too large, maybe you should back off so that you can more ease into where you want to go, okay? And the I is an integrator, which is integrating sort of the whole history of where you've come and gone. And there are means and mechanisms to tune these PID controllers, or you can have different variations of them. Those are standard controllers. There's another type of control which would be a more model-based control, which says if you have a reasonable model of your system, so you know your structure looks like this, and you can model it with beam elements, right? And you've got masses on it like this. So you've got a good numerical model of your structure. Then you can design a controller based off of that model, okay? And this starts to get us into other types of controllers, which would be LQR controllers, linear quadratic regulators. This is beyond what I want to be talking to you about, but it's I think you probably have some nice ugly looking integrals that one can integrate, and some brilliant mathematician said, to reduce that integral, this is what you need to do. It involves solving Riccati equations and a number of different things, and this is the gain that you would use that would minimize this function. Okay, so there are some heavy mathematics behind what we can do here. But this is the basic sort of understanding of controls and what we want to do with this and what we can do with this. Are there any questions on controls? This is sort of leading you up to this vast open area. It's a fascinating area and field to get into. And it can go many different ways, from being very basic to very basic and applied to very theoretical, right? Okay. So the last thing on here that I want to cover, the last of these 4 areas that I said made up smart structures, is this idea of actuating devices, okay? And we have here passive control strategies, which would be passive devices they're not controllable. So it's like a shock absorber in your car, but they make them large enough for buildings, okay? But it is what it is, right? You put it in the building and it's not changing the damping that it adds to your structure. That's it. They don't require any power, though, which is very nice, because at least in earthquakes, what's one of the first things that we might think we lose? It's going to be power, right? And any major disaster. And so unless we have a backup power source, we don't want to rely on the protection of our structure on something that won't likely be there when we need it, okay? So these active devices examples again would be like motors, right? Or hydraulic actuators, hydraulic pistons that we can move in and out and articulate. They're controllable, they're fully controllable, which is great, but they can require significant power to operate. In particular, if we're talking about being able to apply the forces we would need to apply to a building, right? These are very large, heavy structures, and even if the forces are a fraction of the weight of the building, we're still talking about very large forces that need to be generated, okay? And so that's what brings us down to this other class, which are the semi-active control strategies and the semi-active control devices. These devices have the positive attributes of both passive and active in that they're controllable. We can control them. And mind you, these are the devices that it's a piston where we're changing the orifice, the size of the orifice, right? To have a variable stiffness or a variable damping device. So they're controllable, but they require little power to operate. All you're doing is changing a valve, okay? So that's something that could operate off of a battery. Okay. So these are, again, some pictures of these actuating devices: an active mass damper, the hybrid mass damper that is somewhere in between there, and then these controllable fluid devices. So this could be a control valve that we're turning on and off, opening. It's wide open or it's shut. When it's wide open, when this piston moves back and forth, right? So the base is attached to one part of your structure, and this is attached, the end is attached to another part of the structure that's moving relative to the base. So this piston moves back and forth, and as it does so, it pushes fluid from one side to the other side, okay? And it pushes it through this valve, okay? So this is how these work then, is all we need to do is change the size of this orifice or the size of the valve, okay? All right. So an alternative to this that I'll show you some more examples are of, and these are some dampers that I have worked with for a number of years now, are MR dampers. So it stands for Magnetorheological Fluid Dampers. Okay, it's this specific type of fluid. That this fluid, MR fluid, it was discovered, was it back in the 50s maybe? And it's essentially, I think this is maybe getting ahead of myself, but it's an oil-based fluid that has iron particles suspended in it. Okay, and so in normal operation, you can push this back and forth and everything's fine. When you put it in a magnetic field, those iron particles line up and they form chains. And now this fluid that you had, this nice fluid that you had, becomes more like a peanut butter. Okay, the viscosity of it increases quite significantly. So going back to here, if we imagine pushing this nice fluid through here, now in this region, you create a magnetic field. Now it's like pushing peanut butter back from one side to the other, okay? And the neat thing about this is when you take away that magnetic field, it goes right back to a fluid, just a nice regular fluid. And that change to the fluid happens in milliseconds. Okay, so I think within 10 milliseconds, that fluid, when energized, those particles line up or they dissipate. So that's a very short period of time when you're talking about 5 seconds for a building to vibrate back and forth. Okay. Okay. So MR dampers, they're a very promising type of semi-active control device. They have low power requirements. They have mechanical simplicity because you're no longer even rotating a valve. You're just creating a magnetic field. How can you create a magnetic field? I suppose you could stand there with a magnet, permanent magnet. Better yet would be, we're engineers, right? So if you had a coil of wire, you could run voltage through a wire and generate an electromagnetic field, okay? They're inherently stable in that they're not adding more energy into the system. They only produce a force when the building is moving, okay? And if we lose all power, if everything goes crazy, if a wire is cut, it's at least a passive damper that's sitting there, okay? So it'll dissipate some energy, okay? They have a high dynamic range, which means the forces between when it's off and when it's on are very large. It can be a factor of 20, okay? And a large operating temperature range, because if you're dissipating energy, you're dissipating it through heat. So in an earthquake, these dampers are going to heat up quite a bit. And so you want fluid that's going to continue to operate while it heats up, okay? All right, but they have yet to be applied in the US to civil structures. They've been applied elsewhere. Again, this is micron-sized polarizable iron particles that are suspended in oil, and we've talked about this, these other aspects on here. This is a picture of an MR damper, and now instead of having that bypass valve, we have this piston that moves back and forth. The pink is the MR fluid, and the MR fluid goes through this small channel, right? So for it to go from one side to the other, it passes through this small channel, and here's a coil of wire, right, that's looped around here. So we create this magnetic field right in this region here, and that's enough to slow things up. That's enough to create larger forces in this system. And this is, these are some hysteretic curves. This is displacement versus force. And as we cycle this thing, as we cycle the damper back and forth, it's hard to see. I apologize for my labeling, but this is for zero current being sent to the damper. We have a force of about 25 kilonewtons, okay? And if we now increase to the maximum current, we can have 200 kilonewtons. We call this a 200 kilonewton MR damper. We then tested this at Lehigh University, where they pushed much faster on these dampers, and we got 250 kilonewtons out of them. So I don't know if we formally changed the name or not, but it's very large forces that we can produce in these dampers. And you can see this is the maximum force as a function of current. And at some point, the current, right, the current is what's creating our magnetic field, and at some point we saturate out, right? So, okay. So these dampers, we had purchased and done some research on some large-scale dampers. They were manufactured by the Lord Corporation. They're about 1.5 meters in length, and they have a stroke of about 0.6 meters, okay? And they're controllable with an 80-volt DC power supply to get good performance, good control. So you could control this with a bank of some car batteries that if there were an external power outage, you could continue to operate these things. These are the three dampers that we had. We've tested them at, and this is the size that you can see from a person. We've tested them at the University of Colorado Boulder and at Lehigh University. They've been tested at the University of Illinois, and I think one is currently at the University of Alabama and University of Maryland, and the third at University of Illinois right now. So they've been tested by a number of different researchers in a number of different applications, but these are the size of a damper that one would want to put into a civil structure. I'm going to quickly go through this, but I wanted to have some appreciation for these damper models and beyond what a typical, so for a typical system identification that we might look at would look at what's the model of this damper given the cases. This is if we have the damper itself with the fluid, and there are a number of different models that we can have of these that use Buchwen models. Hyperbolic tangent model was one that I've really like to use, but these different models, but it's in a bigger system, right? And so you have a displacement velocity or acceleration that's going into the damper, and we're interested in the damper force. And the other thing that we have is a current, right? A current that's going into the damper. But how do we generate that current? We have to generate that current with a pulse width modulated amplifier, right? Because you want to have enough current. So your control computer is sitting here, and it puts out a voltage of 0 to 5 volts, usually, maybe 0 to 10 volts. And that has to go into an amplifier that then puts out, right, it puts out a current, and back in here, it's got that 80-volt battery supply that it's able to push out a much stronger current from, okay? So in modeling all of these, the one thing that we had noticed was this component here, which is the inductance in the MR damper. These might be terms that maybe you're familiar with, maybe you're not. I want to mention them so that you can, again, continue to get this appreciation for how interdisciplinary this idea of smart structures are. Even the basics of what damper force do we get out of this, we have to draw from many other backgrounds or areas. And what's important in your education, right, a broad education is knowing that these different things exist, because we can all go look this up, right? You can go look it up in a textbook or however you choose to go look up this information. So the inductance of the MR fluid coils was of interest, and what we realized was here we're going from 0 volts up to 2.5 volts, okay? And the test was to put the damper for a short period of time with a constant velocity, and during that period of time go from 0 volts to 2.5 volts, okay? And what we see is that, the damper force increases, right? We would expect it to increase. It went from here, this is our current, this is our force over here, but it goes from about 25 kilonewtons up to 205, 210 kilonewtons, right? Just from going from 0 amp to 1 amp. But there's a disconnect because this is the current after the pulse width modulated amplifier, okay? There's some dynamics associated with that, but it takes the force a lot longer than the actual current. We thought that they were proportionally related to one another, but there's something missing in there. And what's missing is it takes more time for that current, that magnetic field, to build up in the MR damper because it's a huge coil of wire. and you're pushing current. It's like trying to push water through a hose, a big hose that's looped up. And you want to push it through in, right, 20 milliseconds? Good luck, right? What do you need to do? You need to push real hard, is what we ended up realizing. But this is what you've got when you just try to push this through, okay? So real quickly through this, we wanted to look at this magnetomotive force that's developed, the magnetic flux on this. I'll go quickly through here. The dynamics of the electromagnetic circuit looks something like this. This is the Laplace domain. Again, these are things that you learn in math and think you won't need to learn otherwise, but this is a dynamic system. This is another way to write it. It's 1/1 plus L over R times S is the Laplace variable, but L and R, L is our inductance, R is our resistance in this coil, okay? And what we said was, that's great. What's the inductance in that coil? The inductance is, we have an inductance that the manufacturer tells us, yep, we measured that as 1 Henry. Those are the units for inductance, right? But the actual inductance that we see is that minus the inductance variation due to eddy currents as you're changing current in this coil. And that eddy current, then we have to go all the way into Faraday's law and look at relationships in Faraday's law to say that, that this electromotive force is related to the change in magnetic flux over time, and this is the eddy current and the change in the current over time, right? Which is all equal to the resistance times the current, okay? And now this is some interesting dynamic relationship that we have down here. But we know it exists, and what we find then is, here's the inductance, and if we put all this into our equations, what we can do is we can now predict this. But it actually works, right? And that's the neatest thing when all these equations, all this math, all this physics, right, from these other disciplines, we can put them together, and it helps us as civil engineers to better predict what we expect to see. And what's neat about that is then this is turning off and turning on different dampers running at a constant velocity, but at different currents, and we can accurately predict. The solid line here is the model and the experimental data that we imagined, and then this is us actually trying to control one of these dampers. So how do we get it to move in the speed we need it to move? We do what's called, well, this is just the regular driven going from 0 to 2.5 amps, but to get it to drop down, we can back drive this thing, and we can hit it at 7.5 amps in a very quick portion of time, and we can get it to drop real quick. And our model can predict what we then actually see in doing this. So ultimately, when we go to apply these dampers to a civil structure, which I hope in the coming years we have this opportunity to do for large, these are the large dampers. The small dampers have been applied for cables, and larger dampers have been applied for larger building models. But to dynamically control these things, we're gonna need to know how to change the force real quick. And we're gonna need to have these models, these accurate models of our devices and of our systems, okay? So these large dampers, again, the ones that we've had, we've tested them. This is a frame. So this is a larger frame that was being tested at Lehigh University. These were actuators pushing on the frame and the damper set up down here. 1, 2, 3, you maybe can't see the damper, but there is an MR damper that's located down here with large hydraulic actuators pushing on the building to simulate the inertial effects of an earthquake, okay? We did some testing we thought, well, what if we put 2 MR dampers underneath a bridge deck? And what if we put them underneath the slow lane where the heavy truck travels typically? And we couple these together. And this is a bridge model that shows, this will be slow motion, a truck driving over that bridge model and the response that we see in that bridge model. And we coupled that in real time to these 2 dampers that were sitting here in the lab. So depending on what motion that model was telling us, we gave that motion to the dampers, and they told us what force to feed back into the bridge model. And we can run some of these neat experiments in the lab. See that one more time. That's in real time as a truck drives over it at 55 miles an hour. That's in slow time. So, okay. And then this is an application that I'm really excited about, and I think we've been working with folks at eDefense in Japan for a number of years, and I think finally we've got there's some more forward motion on this, but this is looking at a base isolated structure and possibly putting MR dampers, some of these large MR dampers, between the base and the foundation of the structure, and controlling the response of this structure in that sense. And there's a number of people that would be collaborating on this, and eDefense has a wonderful base isolated building structure that then we hope we can get into and put some MR dampers on. So that's the information I have on actuating devices, and just a little taster on what are some of the devices that are out there, and what are some of the things that we're looking at. And at this point, we'll go to our second example, which is connected control method for the base isolated seismic buildings. So.
Bueno, este tema en particular a mí me parece sumamente interesante. Me parece que nosotros como ingenieros civiles, si queremos proveer un mejor desempeño en las estructuras, tenemos que empezar a interesarnos por estos temas. Y como decía el profesor, es un lenguaje completamente nuevo, no estamos acostumbrados a esto, pero es muy, muy interesante, y cuando uno lo ve, ya no lo puede dejar de ver nunca más. Es como, uno lo ve en todo lado, lo ve hasta, no sé, hasta los sistemas con los cuales convive uno comúnmente, y entonces se vuelve algo que, bueno, en el caso mío me parece bastante, muy, muy apasionante, la verdad. Entonces, vamos a hablar de esto un momentito. Se trata acerca de tratar de controlar edificios que son adyacentes, que tienen aislamiento en la base mediante el uso de acopladores. Entonces para poder hablar de este tema, a mí me gustaría mostrarles a ustedes lo que involucra esto desde el punto de vista teórico. Entonces hay toda una teoría detrás de esto que le da sustento, y que, en lo que se llama control moderno, tiene que ver con lo que se llama formulación de espacios de estado. A mí me gustaría mostrarles cómo se implementan los sistemas de protección sísmica que el profesor estaba mencionando en el marco de la formulación de los espacios de estado, un poco de control por realimentación de estados, y luego ya entramos en detalle del ejemplo en particular. Es un ejemplo numérico que yo creo que ilustra bastante bien de qué se trata todo esto. Son 4 casos, y la idea es comparar el desempeño de cada uno de estos casos para el caso de un registro en particular, de un sismo en particular. También me gustaría mencionar algunos de los esfuerzos que estamos haciendo de investigación actualmente, que tienen que ver con este tema, y que yo creo que son muy, muy relevantes para el contexto tico también, que yo creo que en los próximos años vamos a empezar a ver más y más de esto. Muy bien, entonces para hablar de esto, yo creo que la manera en la que nosotros nos sentimos más cómodos es mediante la ecuación del movimiento, ¿verdad? A esto es lo que estamos acostumbrados, es una ecuación, un sistema de ecuaciones diferenciales de n grados de libertad, de segundo orden, ¿verdad? Porque tenemos una segunda derivada acá. Entonces, con esta ecuación diferencial básicamente es que resolvemos el problema sísmico. No importa si estamos hablando, no sé, de métodos de historia en el tiempo, si estamos hablando de métodos de, no sé, de espectros de respuesta, por ejemplo. Entonces, la formulación de los espacios de estado lo que intenta hacer es convertir este problema, tomar estas ecuaciones de segundo orden y convertirlas en ecuaciones de primer orden. Entonces, con eso hacemos que el problema sea un poco más sencillo. Y además combinamos esas ecuaciones de primer orden en una única ecuación diferencial vectorial. Entonces uno puede incrementar el problema, la magnitud del problema, digamos la complejidad del edificio, sin que se incremente la complejidad de esta ecuación diferencial vectorial que está acá. Además, esto nos permite lidiar muchísimo mejor con situaciones en donde tenemos múltiples entradas y múltiples salidas. Lo que conocemos en inglés como Multiple Input, Multiple Output o MIMO. Y además podemos incluir efectos no lineales en la estructura sin ningún problema. Entonces, esta formulación es bastante conveniente para enfrentar estos problemas de control. Ahora, cuando hablamos de espacios de estados, estamos hablando de un espacio vectorial, y cuando hablamos de estados, nos estamos refiriendo, en el caso de un edificio, una estructura, nos referimos, por ejemplo, a la aceleración, velocidad y desplazamiento. Esos son los estados del edificio, y eso nos dicen cuál es la situación de movimiento de ese edificio en un determinado momento, ¿verdad? Entonces, como les dije, lo que vamos a tratar de hacer es tomar este modelo y tratar de convertirlo en una ecuación vectorial que contiene n ecuaciones diferenciales, pero de primer orden. Entonces, por ejemplo, lo que podemos hacer es aislar la aceleración acá. Entonces, ustedes ven que la aceleración va a ser función de otros dos estados, que son estos dos, desplazamiento de velocidad, y función de un valor de entrada. En este caso, el valor de entrada es el terremoto, ¿verdad? Entonces, repito, está en función de estados y de valores de entrada. Esta ecuación aún más la podemos expresar de manera vectorial como se ve acá, ¿verdad? Es simplemente una multiplicación de este vector por este, y en ese caso también es una multiplicación vectorial. Entonces, si nosotros definimos un vector de estados de esta manera, le llamamos z, y definimos su primera derivada de esta forma, entonces podemos condensar todo en una sola ecuación vectorial como se ve acá. Entonces, vean que aquí tenemos la velocidad y la aceleración, y esta fila que corresponde a esto que estoy marcando acá es una ecuación diferencial de primer orden, y la segunda fila también. Entonces, la formulación de espacio de estados nos permite lidiar con el problema de esa forma. A esta matriz que antecede a los estados se le llama matriz de sistema. A la matriz que antecede el valor de entrada se le denomina matriz de influencia, y al valor por ejemplo, del terremoto en este caso se le llama vector de entrada. Entonces, ustedes pueden ver cómo esta matriz contiene la información de todas las propiedades dinámicas de la estructura. Es decir, tenemos masa, rigidez y amortiguamiento. Entonces, todas las propiedades de la dinámica de la estructura están aquí. Tenemos una matriz que me dice qué es lo que está afectando o perturbando la estructura, que es la combinación de estos dos. Entonces, podemos condensar todo en lo que se le conoce como la ecuación del sistema. Como tal vez ustedes recuerdan que el profesor estaba mencionando anteriormente, el lenguaje fue desarrollado en el contexto de ingeniería mecánica. Entonces es muy común que la notación que se encuentra en la literatura sea la que se muestra ahí, en lugar de la que estoy usando yo acá. Ahora, esto está hablando de las propiedades de la estructura y el valor de entrada, pero ¿qué pasa con la respuesta? Entonces podemos utilizar una formulación muy parecida, utilizar la misma secuencia o razonamiento lógico y obtener esto. De nuevo, está condensado en ecuación vectorial que tiene ecuaciones diferenciales de primer orden nada más. En este caso en particular yo estoy definiendo los valores de salida de esta forma, pero en realidad pueden ser cualquiera. Aquí estoy diciendo yo, bueno, yo quiero saber, estoy interesado en, no sé, desplazamiento relativo, velocidad relativa y aceleración, pero puede ser cualquier valor de respuesta el que yo quiero poner aquí. Puede ser fuerza incluso. O puede ser velocidades absolutas, no sé, el que uno quiera. Entonces, uno puede condensar, al igual que el anterior, en una sola ecuación y la notación alternativa es la que se ve ahí. Entonces, la estructura que nosotros modelaríamos originalmente con la ecuación del movimiento que mostré al principio se puede condensar en un diagrama de bloques en donde tenemos un valor de entrada, algo que toma este valor de entrada, lo modifica y nos da un valor de salida, ¿verdad? Entonces es un concepto bastante intuitivo, creo yo. Y esto es análogo a lo que en control clásico es muy común de ver, que son las funciones de transferencia, ¿verdad? Que son relaciones de salida e entrada nada más. Y las funciones de transferencia usualmente se usa, no sé, el dominio de Laplace o el dominio de la frecuencia o cualquier otro similar. Entonces, esta es, en resumen, lo que concierne al modelo de espacios de estados. Ahora, ¿cómo aplicar esto con los sistemas? ¿Cómo incorporar los sistemas de protección sísmica acá? Bueno, nada más lo que tenemos que hacer es escribir las ecuaciones del movimiento, como al principio, y seguir el mismo proceso lógico y vamos a obtener lo mismo. No importa si es un sistema pasivo como este, ¿verdad? Que puede ser sistemas donde dependen de la aceleración, como los amortiguadores de masa sintonizados, o de la velocidad, si es un amortiguador viscoso, o si es de desplazamiento, como las riostras de pandeo restringido, que son sistemas que existen. O si se trata de un sistema activo donde tenemos actuadores de diferentes tipos, o un sistema semiactivo en donde cambiamos las propiedades de la estructura en tiempo real. Entonces, no importa cuál sistema de protección queremos incorporar, lo podemos modelar de esta forma. Entonces, como yo les estaba diciendo, podemos utilizar la formulación de los espacios de estados para tratar de modelar y predecir el comportamiento y tratar de diseñar para eso. Ahora, un poco acerca del control de realimentación, en particular con la realimentación de estados, porque el profesor estaba hablando de Ph.D. control. Esto es ligeramente diferente, pero es el mismo concepto de que uno toma un valor de respuesta y lo alimenta de nuevo a la estructura para tomar alguna decisión. Entonces, la idea fundamental es que podemos escribir cualquiera que sea la fuerza de control como un vector que me va a ubicar, me va a dar la ubicación del dispositivo de control en la estructura, multiplicado por la fuerza o la magnitud que se genera en el dispositivo de control, y se asume que existe una ley de control dada por esta ecuación. En este caso acá se le denomina ganancia de control. U es el vector de fuerza que estamos aplicando para controlar la estructura, y Z son simplemente los estados de los cuales hablaba al principio. Entonces, en lugar de tener un sistema de lazo abierto, open loop, ahora tenemos un sistema de lazo cerrado, y ya cerramos aquí y tenemos el caso del closed loop. De nuevo, entonces ven, tenemos toda la información dinámica de la estructura acá, tenemos información acerca del terremoto y tenemos información acerca de la fuerza de control que estamos aplicando. Esa información la exportamos al controlador, que nos va a decir qué hacer con eso. Y eso se alimenta en la estructura de nuevo y sigue el ciclo indefinidamente hasta que se logra el objetivo. Entonces, para ejemplificar cómo es que esto se hace, les presento un ejemplo acá, que consiste en 2 edificios, son modelos sencillos de 4 grados de 4 pisos, 5 grados de libertad cada uno. 2 edificios adyacentes y que potencialmente pueden estar conectados con un sistema de acople. Entonces las propiedades de estos 2 edificios son las que se muestran acá. Y para este caso en particular estoy haciendo nada más la diferencia a nivel de la base. No sé, por ejemplo, que tenga diferentes sistemas de aislamiento en la base, o que tenga más aisladores aquí que acá, o no sé. Pero lo importante es que son valores diferentes y por lo tanto me van a generar respuestas diferentes. Las superestructuras de los 2 edificios son exactamente la misma. Entonces, como se ve ahí. Para mostrarles este ejemplo, lo que estoy usando es un registro del terremoto del centro que tiene historia del tiempo y tiene ese contenido de frecuencias que se ve ahí. Este terremoto del centro es escalado porque el ejemplo que les estoy presentando está basado en un ejemplo que se hizo de un modelo a escala. Entonces se escaló en el tiempo para poder considerar los efectos de escala también. Se estudian 4 casos, o les presento aquí 4 casos, que son cuando los edificios están desacoplados, tienen aislamiento en la base, cuando están desacoplados y tienen aislamiento en la base, pero se les añade un amortiguador adicional, cuando están acoplados con un dispositivo pasivo y cuando están acoplados con un dispositivo activo. Entonces, como les decía, la idea es comparar qué es lo que pasa en cada uno de estos ejemplos y ver si el desempeño de estos edificios mejora o no. El modelo estructural es el de siempre. En este caso estoy simplemente condensando las matrices de masa, rigidez y amortiguamiento en una sola, es decir, estoy diciendo que mis 2 edificios son un solo sistema, ¿verdad? Y los valores de desplazamiento, velocidad de aceleración también son los de costumbre. Para modelar esto es muy común usar MATLAB, el módulo de análisis de sistemas que se llama Simulink, y se usan estos diagramas de bloques. Entonces ustedes ven aquí que aquí está la aceleración del terreno, aquí está el modelo de formato de espacios de estado con sus respectivas matrices. Tenemos también un bloque para el aislamiento de la base, por si quisiéramos considerar algún comportamiento no lineal, y un bloque para el acoplador. En este primer caso es 0 porque los edificios están desacoplados, entonces aquí no hay nada. Bien, entonces esta es una comparación de los casos 1 y 2. Aquí lo que estoy mostrando son las aceleraciones en la parte izquierda y los desplazamientos en la parte derecha para edificios A y B, ¿verdad? Respectivamente. Entonces ustedes pueden ver que cuando uno aplica el aislamiento en la base, lo que pasa es que se incrementan los desplazamientos en el primer piso, ¿verdad? Hay una concentración de la deformación acá y entonces se incrementan los desplazamientos. Y los desplazamientos relativos de los pisos superiores son bastante pequeños. Aquí cuesta un poco verlo, pero son como 2 órdenes de magnitud más pequeños. Entonces, como esta situación ocurre, es muy común tratar de controlar este problema a través de añadirle algún tipo de amortiguador en la base. Entonces, por ejemplo, el caso 2 es los edificios desacoplados con un amortiguamiento adicional en la base. Entonces ustedes pueden ver, más o menos, no sé si se ve bien, pero que hay una reducción de la respuesta de los desplazamientos en la base, que es lo que andamos buscando. Pero la consecuencia negativa es que se aumentan las aceleraciones en todas las estructuras, en todos los pisos para las 2 estructuras. Entonces, por ejemplo, es muy común que uno quiera aislar los edificios como un hospital, ¿verdad? Uno quiere proteger la estructura y entonces aplicamos aisladores, pero lo que pasa es que si nosotros para controlar desplazamientos de ese aislamiento añadimos amortiguamiento, entonces vamos a comprometer las aceleraciones. Y en un hospital esto puede ser crítico porque tenemos equipo. Y el hospital no puede salir de operación. Entonces, ¿es un desempeño adecuado o no? ¿Verdad? Entonces, eso hay que considerarlo. También esto nos lleva a utilizar el método de control por acoplamiento, que es el caso 3, en donde ya estoy incluyendo aquí un acople pasivo. Para hacer este ejemplo más sencillo, entonces estoy considerando un acoplador lineal que tiene solo un valor de rigidez y un valor de amortiguamiento dado. Y la fuerza que genera este acople en ambas estructuras va a ser proporcional a la rigidez y al amortiguamiento multiplicado por los desplazamientos y velocidades relativas de este último piso. Es un modelo bastante sencillo y podemos modelarlo como una ley de control, ¿verdad? Entonces, nuestra ley de control va a ser esta acá, que es simplemente un vector, y multiplicado por los estados. Entonces, esa es nuestra ley de control y podemos hacer uso del modelo que les estaba mencionando anteriormente. Ahora, la pregunta es cómo escoger K y C. Existen múltiples maneras de optimizar esto dependiendo de cuál es el objetivo que uno tiene, pero por ejemplo yo aquí si utilizo gráficos de contorno puedo llegar fácilmente a un valor como este. Entonces puede utilizarse otras técnicas, por ejemplo algoritmos genéticos para tratar de optimizar el valor de estos parámetros de acá. Entonces vean lo que pasa cuando aplicamos el acople pasivo. Logramos reducir los desplazamientos a nivel de piso inferior o a nivel de la base y también logramos reducir las aceleraciones en todos los pisos. El gráfico en azul son los edificios aislados más amortiguamiento adicional que estaba mostrando en el caso 2. Y los gráficos en rojo es para los edificios acoplados. Entonces hay un gran beneficio de utilizar esta técnica. Pero no solo visualmente, a nosotros los ingenieros nos gusta ver más los números, entonces se pueden definir parámetros para decidir si esto está bien o no. Entonces aquí cuesta un poco leerlo, pero este es el desplazamiento máximo experimentado. Y esta es la aceleración máxima experimentada. Y estos otros dos parámetros de acá son la raíz cuadrada del promedio de los valores de cada uno de los parámetros que estudio. Por ejemplo, desplazamientos o aceleraciones. Y están estos factores para ponderar si alguno de estos valores de respuesta me interesa más que el otro. Y para este caso en particular estoy usando todos los valores de ponderación iguales a 1 para simplificar el problema. Pero entonces, como les decía, cuando tenemos los edificios aislados y le añadimos amortiguamiento, sí bajamos un montón los desplazamientos, pero se nos incrementan las aceleraciones y esto no es algo deseable. Y cuando aplicamos el acople pasivo, logramos bajar aún más con respecto, bueno, estos porcentajes debo decir que son con respecto al caso original, es decir, con respecto al caso 1. Entonces, 41% de reducción con respecto al caso 1. Este parámetro se mantiene casi constante y estos dos bajan. Entonces, estamos con un desempeño que es considerablemente mejor que el caso cuando estamos agregándole amortiguamiento adicional pasivo, ¿verdad? Ok, entonces el último caso que quiero presentar es el del acople activo. El acople activo, como decía el profesor, tiene la capacidad de no solo disipar energía, sino de introducir energía dependiendo de lo que yo quiera hacer. Entonces eso suena un poco peligroso. Estamos diciendo, estamos introduciendo energía en el sistema, pero si se hace con suficiente cuidado, entonces puede lograrse resultados satisfactorios. Entonces, lo que se busca es minimizar, cuando hablamos de control óptimo de estado, estamos hablando de un controlador que minimiza esta función de costo. Entonces lo que tenemos aquí es unos estados que multiplican una matriz Q que penaliza el valor de cada uno de esos estados. Es decir, si a mí me interesa reducir el desplazamiento, entonces en esta Q voy a penalizar el desplazamiento. Y tenemos la parte que penaliza el costo de hacer eso. Por ejemplo, no sé, qué tanta energía necesito para que el actuador me genere esa fuerza. Entonces está penalizado acá. Y el control LQR, que es el regulador lineal cuadrático, minimiza esta función de costo. Está sujeto a las restricciones que se muestran acá. Y entonces la ganancia de control que obtenemos al resolver este problema nos va a dar el control óptimo. Esto fue resuelto, como decía el profesor, hace poco fue resuelto por matemáticos muy brillantes, ¿verdad? Que llegan a la conclusión de que esto es la solución de ese problema, se obtiene de esta manera. Y no vale la pena entrar en detalles, sino lo que vale la pena es decir que MATLAB lo hace por uno. Entonces, no hay que preocuparse de eso. MATLAB tiene un módulo de control que permite calcular esta ganancia para ese problema en particular. Entonces, ya podemos aplicar nuestra matriz de ganancia aquí, en lugar de la matriz de ganancia pasiva que teníamos anteriormente. Ahora, como les decía anteriormente, yo puedo penalizar lo que a mí me interesa penalizar. Por ejemplo, esta matriz Q está asociada a cada uno de los estados, y si los estados eran, por ejemplo, desplazamientos y velocidades, entonces, y aceleraciones, entonces estos estados de aquí son esta penalización es correspondiente a los desplazamientos del edificio A, esto de aquí a los desplazamientos del edificio B, y también aceleraciones de A y B. Entonces, por ejemplo, yo digo, no, los desplazamientos en la base son indeseables, entonces voy a castigarlos más. Entonces le pongo un valor, ¿verdad? Esto no necesariamente tiene las mismas unidades, sino que es consistente con el problema del control. Y luego quizás me interesa penalizar las aceleraciones en último piso, entonces yo voy a decir, bueno, también lo voy a penalizar, tal vez no tanto como los desplazamientos, pero un poquito, entonces lo hago de esa forma. Y como solo tengo un controlador, entonces solo tengo un escalar para la optimización de la función de costo. Pero lo que yo quiero acá enfatizar es que soy yo el que tomo la decisión de cuál es el parámetro que quiero penalizar. Es decir, no sé, las necesidades del cliente pueden ser las que sean, entonces uno puede decirle, bueno, sí, yo voy a darle este desempeño a usted, en lugar de decirle, bueno, no sé qué va a pasar, ¿verdad? Eso es una característica de poder controlar las cosas. Entonces, a la hora de comparar, podemos ver el caso verde. No se ve muy bien por la resolución, pero el caso verde también minimiza o reduce los desplazamientos en la base y reduce las aceleraciones en todo, digamos, en toda la estructura también. Entonces, de nuevo con la tabla podemos comparar de una mejor manera. Esto es lo que teníamos hasta ahora y llegamos hasta este punto en donde tenemos una reducción dramática aquí del valor de desplazamiento máximo, casi un 43%. Un comportamiento bastante parecido a lo largo de estos tres casos, pero estos otros dos también son mejores. Entonces el comportamiento en general es bastante satisfactorio. Y debo decir que bueno, yo me detuve en 700, pero pude haber puesto más castigo a esos valores, simplemente para ejemplificar cómo funciona el método. Esfuerzos adicionales de investigación que estamos haciendo es tratar de aplicar este concepto en estructuras más realistas. Este es el modelo del edificio del E-Defense que estaba mencionando el profesor. Incluir amortiguadores MR dampers, que son semiactivos y tienen la ventaja de que no son estables por naturaleza, entonces son muy prometedores y requieren poca energía. También considerar control probabilístico, porque en este ejemplo yo les estaba mostrando un ejemplo de control en el cual yo conozco todo lo que necesito conocer de la estructura, pero eso puede ser no cierto si yo tengo daños en sensores, por ejemplo, o si alguno de los valores que yo quiero medir no es tan fácil de medir. Y esto implica utilizar otros conceptos de control, como los observadores, que esto también es todo un tema, ¿verdad? Y el más utilizado es el observador de Kalman y Busi. Bien, entonces este es el ejemplo que tenía para ustedes. Si tienen alguna pregunta, con mucho gusto.
So I have just a few brief remarks then in conclusion, right? Okay. So again, these smart structures, what we've talked about are some smart structures. The potential for the start of looking at smart structures and they're engineered structural systems with these integrated sensor networks, information processing units, controllers, actuating devices that essentially can adapt and react to their environments, right? They require engineers that are strong in interdisciplinary backgrounds, civil, mechanical, electrical, and are engineers in civil structural engineering that understand and are able to communicate with their counterparts in these other disciplines. Okay. Smart structure concept, it continues to rapidly evolve, and maybe more so now. It's evolving with the increases in technology. Okay. I believe it's a very rewarding area of study, and there are many advances that are yet to be made. So I think there's a lot of potential. There are a lot of challenges that have been identified but need to be solved. And there are probably a lot more challenges that haven't even been identified. So there's great potential for the future for this. And ultimately, I think smart structures have the promise to provide safer and more resilient infrastructure in a world that has limited resources. So I think this is a concept and idea that is needed by society, and it's an area that I think you as engineers moving forward can look at and can make great contributions to the field in. So with that, I would say I want to thank you very much for allowing us the opportunity to come and talk to you about smart structures, but for inviting me to again come to Costa Rica. It's a very rewarding experience for me, and I think in all the discussions that I had, the research and studies that are going on here at the university are really amazing, and I hope that we can grow in these collaborations. And I want to thank Pablo for all of his efforts in arranging what he had made, and all the faculty and researchers that had met with me earlier today. I really appreciate the time that you've taken, and really appreciate hearing about everything that you're doing. So with that, I would say thank you, and if you have any questions, you can come on up afterwards, and otherwise, have a good evening.